In this presentation we examine conductors in electric field. We start with the discussion on how to determine an electric field due to a charged conductor both outside the conductor and inside its cavities. Based on the properties of the electric field due to charged conductors, we will also describe how a presence of an electrically neutral conductor changes the field if placed in electric field. In order to characterize the behavior of charged conductors, we introduce the concept of capacitance, describing the relation between the charge of the capacitor and its potential. We consider a special class of conductors called capacitors as well, designed to store large amount of charge if a relatively small voltage is applied for them. We determine the energy of a charged capacitor, which helps to derive the basic equations for the energy density of electrostatic fields. Then we calculate the electric force exerted on charged conductors by the electrostatic field, and we discuss how this type of force is used to measure the amount of charge or voltage with measuring instruments called electrometers. Finally, we present the method of images, which is a simple approach to determine the electric field and force produced by point or line charges near conductors with various geometries exhibiting some symmetry. In order to discuss the behavior of conductors in electric field, we need to study the distribution of electric charge, the electric field and the potential in them. Let us suppose that a charged metallic conductor is in equilibrium state, that is, its electric charges are at rest from phenomenological point of view. Then the previously presented laws of electrostatic related to electric field strength, potential and charge can be applied in simple examples and thought experiments where we can draw the following conclusions. The first conclusion tells us that in the case of equilibrium, the electric field strength E is equal to 0 and the electric potential phi is constant inside a conductor. We can prove this statement by supposing that some excess charge distributed over the surface of the conductor produces a non-zero electric field inside the conductor. Then the electric field will act on the charge carriers, that is the electrons inside the conductor, and accelerates them in a given direction. The current due to the motion of charge carriers results in a spatial redistribution of them, reducing the electric field till it vanishes completely. The redistribution of charge or the establishment of electrostatic balance is an extremely short process. For the vanishing electric field strength E inside the conductor, the negative gradient of the electric potential phi is equal to 0, that is, the potential phi must be constant inside the conductor. The second conclusion states that in the case of equilibrium, the electric field strength E must be perpendicular to the outer surface of the conductor. For if the vector E was not perpendicular to the surface, then it would have not only a normal component but a tangential component accelerating the charge carriers on the surface. As a result, the charge carriers would be displaced over the surface by the electric field, producing a current over the surface. Since there is no current in equilibrium, the vector E must be perpendicular to the surface of the conductor with a vanishing tangential component, that is, the surface of the conductor is an equipotential surface. But we have already seen that the electric potential inside the conductor is constant, and the whole conductor is then an equipotential domain. We also have a third conclusion stating that in equilibrium an excess electric charge is distributed over the outer surface of a conductor. This conclusion follows from another thought experiment. Let us consider a closed Gaussian surface S inside a conductor close to its outer surface. Since there is no electric field inside the conductor in electrostatic equilibrium, the flux phi sub E of the electric field strength E passing through the Gaussian surface S vanishes. Then it immediately follows from Gauss' law that the total charge enclosed by the surface S is equal to 0. This statement holds for any closed surface of arbitrary size and shape inside the conductor. As a result, in the electrostatic equilibrium there is no excess charge inside the conductor, and the charge is distributed over its surface, and this distribution is described by a given surface charge density sigma. These conclusions drawn from the thought experiments can be demonstrated by the following experiment. First, we give some amount of electric charge to a metal box with a hole on it which is electrically insulated from its environment. If we bring an electrically neutral metal sphere into contact with the outer surface of the metal box and touch the plate of a discharged electroscope with the metal sphere, then the electroscope will show that the metal sphere attained charge. However, if we bring the electrically neutral metal sphere into contact with the inner surface of the metal box, then the electroscope will indicate that the metal sphere remained neutral, that is, it did not attain any charge. In the second experiment, we give some electric charge to the metal sphere and bring it into contact with the outer surface of the electrically neutral metal box. Then we touch the plate of the electroscope with the metal sphere and the electroscope will show that the sphere remained charged. However, if we bring the charged metal sphere into contact with the inner surface of the electrically neutral metal box, then the electroscope will indicate that the metal sphere became neutral, that is, it lost all the charge. The result of the experiment shows that when the metal sphere is brought into contact with the outer surface of the metal box, then the sphere will either attain or keep some amount of charge, since the sphere and the outer surface of the box forms one system and the sphere is the part of the outer surface of the system. When the metal sphere is brought into contact with the inner surface of the metal box, the sphere either loses all its electric charge, which will move to the outer surface, or does not attain electric charge at all, since the sphere and the inner surface of the box form one system. If we examine the electric field inside a cavity of a charged conductor, then we will find the following. In equilibrium, the electric field vanishes inside a cavity of a charged conductor and no electric charge can be distributed over the surface of the cavity. We can prove this statement by considering a Gaussian surface S inside the conductor where the surface encloses the cavity. We have already seen that there is no electric field in a charged conductor in equilibrium, and any excess charge is always distributed over its outer surface. Since the electric field strength E is equal to 0 at any point of the surface S, Gauss' law tells us that the total electric charge Q must be 0 within the volume enclosed by the surface S. The condition of vanishing net charge within this volume only demands that either there is no electric charge within the volume at all, or the volume contains an equal amount of positive and negative charges. In order to see whether positive and negative charges can exist over the surface of the cavity of the charged conductor in equilibrium, let us suppose that some positive charge is distributed over a part of the surface of the cavity. Then there must be the same amount of negative charge distributed over another part of the surface of the cavity, giving 0 net charge within the volume enclosed by the surface S. The charge distributed over the surface of the cavity produces an electric field E in the cavity. The electric field lines must start at the positive charges and terminate at the negative ones because there are no free charges in the cavity. Let us consider a closed curve C inside the conductor intersecting the cavity. We can calculate the line integral of the electric field E along the section of the curve C between the positive and negative charges in the cavity, which is non-zero. When we perform the integration along the part of the curve C in the conductor where the electric field vanishes, we obtain 0. The line integral of the electric field E along the closed curve C given by the sum of the two integrals does not vanish, that is, the curl of the field E is non-zero. However, this result contradicts the fact that the curl of an electrostatic field vanishes, that is, its cyclic integral is equal to 0, which forbids the presence on electric charges distributed over surface of the cavity, proving the statement. We note that a cavity in a charged conductor can still contain electric charges in equilibrium, provided some charge distributed over an insulator or a charged conducting material insulated from the conductor is placed into the cavity. Now we will study the electric field due to the electric charge distributed over the surface of a conductor. We have already determined the electric potential of a field produced by a given distribution of electric charge over a surface in general case. Let us start with a simple example, where we calculate the electric potential produced by a uniformly charged conducting spherical shell S of radius R at a point P at the distance r from the center O of the sphere. Since the distribution of the electric charge over the surface of the spherical shell is uniform, the surface charge density sigma is constant and equal to the total charge Q of the shell divided by the surface area of the sphere, that is 2 pi times R squared. For a given surface charge density sigma, we found that the electric potential phi at the point P is equal to 1 over 4 pi times the vacuum permittivity epsilon naught, times the surface integral of sigma divided by the distance r prime of the area element ds at the point P prime from the point P, over the charged surface S. In order to determine the area element ds in the integral of the potential phi, we consider a spherical annulus or ring generated by rotating the arc of the length R times d theta about the axis passing through the points O and P. Here d theta is an infinitesimal angle measured in the vertical plane passing through the axis of rotation. Then the area of the spherical annulus of infinitesimal width can be chosen as the area element ds, which can be written as the width R times d theta, times the circumference 2 pi times R times the sine of the angle theta between the line sections OP and OP prime. This gives 2 pi times R squared, times sine theta times d theta. If we substitute the expressions obtained for the surface charge density sigma, the area element ds, and the distance r prime between any point P prime of the area element and the point P, we have 1 over 4 pi times epsilon naught, times the integral of Q divided by 4 pi times R squared, times 2 pi times R squared times sine theta divided by the distance r prime. We can determine the distance r prime between any point P prime of the annulus and the point P by applying the law of cosines for the triangle OP prime P, which tells us that r prime is equal to the square root of r squared plus R squared, minus 2 times r times R times cosine theta. Then the potential can be written as q over 4 pi times epsilon naught, times the integral of sine theta over 2 times the square root of r squared plus capital R squared, minus 2 times r times capital R times cosine theta, with respect to theta from 0 to pi. If we introduce the variable x defined by r squared plus capital R squared, minus 2 times r times capital R times cosine theta, then we can write the differential of x as 2 pi times r times capital R times sine theta, times d theta. By substituting this variable into the integral, we obtain q over 4 pi times epsilon naught, times 1 over 4 times r times capital R, times the integral of 1 over the square root of x with respect to x. The lower and upper limits of the integral are x evaluated at theta equals to 0 and pi, respectively. Now we compute the definite integral, which gives 2 times the square root of x, and we can write the potential as q over 4 pi times epsilon naught, times 1 over 2 times r times capital R, times the square root of r squared plus capital R squared, minus 2 times r times capital R times cosine theta, evaluated at theta equals to 0 and pi. If we substitute the lower and upper limits into the equation, then the expression in the brackets leads to the square root of r squared plus capital R squared plus 2 times r times capital R, minus the square root of r squared plus capital R squared minus 2 times r times capital R. As a result, the electric potential phi at the point P at the distance from the center O of the uniformly charged spherical shell of radius capital R and total charge Q, can be written as the total charge Q over 4 pi times epsilon naught, times the difference between the magnitude of the distance r plus the radius capital R and the magnitude of r minus capital R, over 2 times r times capital R. We can expand this expression and write the potential as 1 over 4 pi times epsilon naught, times the total charge Q divided by the distance r, if the distance r is greater than or equal to the radius capital R, and 1 over 4 pi times epsilon naught, times the total charge Q divided by the radius capital R, if the distance r is less than the radius capital R. The plot of the electric potential as a function of the distance r shows that phi is constant within the uniformly charged spherical shell, and it is inversely proportional to the distance outside the spherical shell. Now we derive the electric field strength from the potential obtained here. The electric potential due to a uniformly charged spherical conducting shell is constant inside the shell and inversely proportional to the distance outside the shell, which is a spherically symmetric function about the center of the shell. Then we can use a spherical coordinate system with its origin at the center of the spherical shell to describe the electric field strength E given by the negative gradient of the electric potential phi. If we write the gradient of the scalar function phi in spherical coordinates, then we immediately see that the polar and azimuthal components of the gradient vector vanish due to the radial symmetry of the potential. The electric field strength E at a given point has the magnitude of 1 over 4 pi times epsilon naught, times the total charge Q of the shell divided by the square of the distance r between the origin and the point, and points in the radial direction. Here the basis vector E sub describing the radial direction r is simply equal to the position vector r pointing from the origin to the given point, divided by its length. As a result, we regain the expression derived when we computed the electric field strength for a spherical shell of a uniform surface charge by applying Gauss' law. If we inspect this result with the electric potential and the magnitude of the electric field strength plotted as a function of the distance from the center of the shell, we can conclude the following. The electric field produced by a uniformly charged conducting spherical shell of total charge Q outside the shell is the same as the electric field produced by a point charge Q located at the center of the shell, and vanishes inside the shell where the potential is equal to the potential on the surface of the shell. We note that when we determine the electric field due to a uniformly charged sphere of total charge Q, we saw that the field outside the sphere is also the same as the field produced by a point charge Q located at the center of the sphere. Essentially, we can replace both the uniformly charged conducting spherical shell and the uniformly charged sphere by a point charge of the same charge, when we study the electric field outside the shell or the sphere. In fact, this statement can be generalized for any spherically symmetric distribution of charge within a finite volume by applying Gauss' law for a spherical Gaussian surface enclosing the given volume with the center at the center of the spherical symmetry. We have studied the electric field due to a uniform surface charge distribution in a conductor. In the most general case, the distribution of electric charge over the surface of a conductor is not uniform, that is, the surface charge density sigma defined by the derivative of the charge Q with respect to the surface area S can change over the surface. We can experimentally verify that the surface charge density and the electric field strength is greater where the surface of a charged conductor is more curved. If we bring electric charge on the conductor made of a metal cylinder and a metal cone on its top as seen in the figure, then a non-uniform electric field is produced by the charge over the surface of the conductor. We can determine the strength of the electric field at different points of the surface, let us say at the points A, B and C where the surface has different curvature. If we bring an electrically neutral metal sphere into contact with the conductor at the point A, and then touch the plate of an electroscope with the sphere, the device will indicate that the sphere attained some charge. If we recharge the conductor so that it has the original amount of charge and discharge the metal sphere, then we can touch the conductor at the point B with the electrically neutralized sphere, and test the amount of attained charge with the uncharged electroscope. We can recharge the conductor and discharge the metal sphere again, and we repeat the experiment by bringing the metal sphere into contact with the conductor at the point C. Then the metal sphere will attain a given amount of charge, as indicated by the electroscope. A comparison of the results of the three cases shows that the amount of charge attained by the metal sphere is the smallest in the first case because the point A is on the flat bottom of the conducting cylinder. More charge is brought from the point B to the sphere in the second case, where the point B is on the curved surface of the cylinder. The greatest amount of charge is attained by the sphere in the third case, since the point C is at the top of the conducting cone. In the next step we will determine the explicit relation between the electric field due to the charged conductor and the surface charge density on the conductor. Let us consider a small cylinder intersecting the surface of a charged conductor as seen in the figure. Since the electric field strength E vanishes within the conductor, it gives a contribution to the electric flux passing through the cylinder only outside the surface of the conductor. If the cylinder is small enough, then the electric field lines emanating from the surface of the conductor in the normal direction remain parallel with the curved surface of the cylinder and they pass through only its top. By considering this cylinder as a Gaussian surface, we can apply Gauss' law stating that the surface integral of the electric field strength E over the cylinder is equal to the total charge Q enclosed by the cylinder over epsilon naught. On the one hand, if S is the surface area of the top of the small cylinder, then the surface integral is equal to the magnitude of the electric field strength E perpendicular to the top, times the surface area S. On the other hand, the total charge Q is given by the surface charge density sigma over the surface of the conductor times the area of the intersection of the surface of the conductor and the cylinder, which is also equal to S. Then the magnitude of the electric field E produced by the electric charge distributed over the surface of a conductor is equal to the ratio of the surface charge density sigma to the vacuum permittivity epsilon naught. If we compare this result with the one obtained for the electric field due to a uniformly charged infinite plane, we can see that the magnitude of electric field strength is 2 times less for the infinite plane than the one for the charged conductor. The explanation of this fact is simple. The charges in the vicinity of a given point of the surface of a charged conductor produce a local electric field in both sides of the surface, which is given by the surface charge density sigma around that point over 2 times epsilon naught. However, the rest of the charges distributed over the whole surface also gives a local contribution to the electric field, which is equal to the same surface charge density sigma over 2 times epsilon naught. As a result, the total electric field at the given point is equal to 2 times the local field, that is sigma over epsilon naught outside the conductor, and vanishes within the conductor. We can demonstrate the inverse proportionality between the electric field strength and the curvature radius of the surface of a charged conductor with the following simple example. Let us consider two small conducting spheres of radii r1 and r2 connected by a long conducting wire. If we bring electric charges into this system, then both the spheres will attain some charge. Since the surfaces of conducting spheres in contact represent an equipotential surface, we can write the electric potential phi over the surface of the first sphere as 1 over 4 pi times epsilon naught, times the total charge Q1 attained by the sphere divided by its radius r1, which is equal to the electric potential phi over the surface of the second sphere, that is 1 over 4 pi times epsilon naught, times the total charge Q sub 2 attained by the sphere divided by its radius r sub 2. It follows from this equation that the ratio of Q sub 1 to R sub 1 is equal to the ratio of Q sub 2 to R sub 2, or Q sub 1 over Q sub 2 is equal to R sub 1 over R sub 2. This relation tells us that the amount of electric charge attained by each conducting sphere is proportional to the radius of the sphere. Then we immediately see that the surface charge density over each conducting sphere given by the ratio of the total amount of charge attained by the sphere to the surface of the sphere, is inversely proportional to the radius of the sphere. That is, the ratio of the surface charge density sigma sub 1 over the first sphere to the surface charge density sigma sub 2 over the second sphere, is equal to the ratio of Q sub 1 divided by 4 pi times R sub 1 squared to the ratio of Q sub 2 divided by 4 pi times R sub 2 squared. By substituting the expression obtained for the ratio of the total charges into this equation gives R sub 2 over R sub 1. Since the magnitude of the electric field strength produced by a charged conducting surface is equal to the surface charge density over the surface divided by epsilon naught, we conclude that the magnitude of the electric field strength E sub 1 for the first sphere divided by the magnitude of the electric field strength E sub 2 for the second sphere, is equal to the ratio of the radius r sub 2 of the second sphere to the radius r sub 1 of the first sphere. In other words, the electric field strength is inversely proportional to the radius and the field strength is greater over the parts of conductors having more curved surface or smaller curvature radius. We note that the distribution of the electric charge over the surfaces of the spheres is not strictly symmetric because the charge on one sphere changes the distribution of charge over the other sphere and vice versa. In this figure we show the electric field produced by a charged conductor with flat faces and sharp edges where the continuous lines mean the electric field lines, and the equipotential surfaces or lines are represented by dashed lines. The field lines emanating from the edges indicate a very strong electric field at the edges. We can also see that the profiles of the equipotential surfaces closer to the surface of the conductor are more like the profile of the surface of the conductor, which is itself an equipotential surface. This example shows that the electric field close to the tip of a sharp conductor can be strong enough either to ionize or polarize the gas molecules of the air in the vicinity of the tip. When it occurs, the ions of charge opposite to the charge on the conductor or electric dipoles are attracted to the charged tip and neutralized on it, reducing its charge or attaining a tiny part of the charge on the conductor. However, ions with like charge are accelerated in the opposite direction by the strong electric field, that is, the charge accumulated at the pointed end of the conductor will repel them. These ions drag the neutral gas molecules along and together produce a detectable motion, that is an air flow around the tip of the charged conductor, known as electric wind. As a result, the conductor loses charge since charges emanate from the tip and exit with the electric wind. This phenomenon is called electric point effect. In order to demonstrate the electric point effect, we present the following experiments. If we attach a tip to the top of the cone of the metal container used in one of the previous experiments and the whole conductor is continuously charged through a conducting wire, then the flame of a candle placed in the front of the tip is pushed away from the tip by the electric wind. If the effect, that is the air flow bending the flame, is strong enough, then it can even extinguish the candle. Since the charge exiting from the conductor through the wind is compensated by recharging the metal container through the wire, the electric point effect can be maintained and the electric wind will continuously blow in the direction of the candle. In another experiment, the action-reaction force pair is applied on a continuously charged fan, where the action is the repulsive force exerted by the tips of the four metal blades of the fan due to the electric point effect, and the reaction of the action keeps the fan spinning. In the next experiment we can demonstrate that the charged conductor A with a tip will lose a given amount of charge, whereas an electrically neutral conductor B placed in the front of the tip will attain like charges in the electric wind originating from the tip. This effect is not a simple separation of charge because the conductor B will keep the attained charge even if the conductor A is removed from its vicinity. We can invert the direction of the process by charging the conductor B and place the electrically neutral conductor A with its tip close to the charged conductor B. The charge on the conductor B causes a separation of charge on the conductor A, and its tip will obtain opposite charges. A given amount of this opposite charge will exit from the conductor through the electric wind while like charges remain there, and as a result, the conductor A attain like charges. It follows from these findings that if we want to prevent charge from leaving a charged conductor through an electric wind or discharge, then the surface of the conductor need to be smooth enough so that we can avoid the occurrence of the electric point effect. However, this effect can also be important in practical applications of very strong electric fields, as we will see in the next examples. The first example is the field emission microscope. The photo shows the tube of a field emission microscope, and a schematic diagram of the device can be seen in the left-hand side. Its operation is based on the effect of the very strong electric field produced close to the extremely sharp tip of a metal pin. The pin is placed in an evacuated space enclosed by the tube, and its very fine tip with a curvature radius of about 10⁻⁷ meter is used as a cathode. The strong electric field with the field strength between 10 to 9 and 10 to 10 volt per meter draws electrons from the tip of the cathode held at a large electric potential. The electrons emitted from the cathode are accelerated in the direction perpendicular to the surface of the pin by the huge potential difference between the pin and the fluorescent layer on the inner surface of the tube. The electrons traveling along the field lines collide with the tube and produce a bright pattern on the fluorescent screen, as seen in the figure. These patterns represent a magnified image of the crystal structure of the pin or the molecular structure of any material sample covering the tip of the pin. The magnification is proportional to the ratio of the curvature radius of the fluorescent screen on which the image is formed to the radius of the tip. For field emission microscopes, the magnification may reach up 1 million times the scale of the sample, but we can achieve even 10 times more magnification with field ion microscopes. Field ion microscopes work with low pressure helium gas instead of vacuum, and the polarity of their pin is reversed, that is, the pin is used as an anode. The helium atoms colliding with the tip of the pin become ionized by losing one electron, and the positively charged ions traveling from the tip to the bulb will produce the magnified image on the screen with a much higher resolution than the one obtained with field emission microscopes. The next example for applications utilizing the electric point effect is an electrostatic machine producing high statics voltages, that was designed by Robert J. van de Graaff, an American physicist, and it is known as van de Graaff generator. A specimen of this apparatus is seen in the photo, and this schematic diagram will help us to understand its working principle. A rubber belt, sometimes made of silk or other elastic dielectric material, runs between two rollers driven by an electric motor. Due to the point effect, the belt attains charge from the tip held at the potential of couple thousand volts, and the charge is transferred by the moving belt into a hollow metal sphere, also known as dome. The original design of the generator uses triboelectric effect between the roller and the belt to separate charges, which causes a strong buildup of charge on the roller and opposite charge on the belt. Instead of a charged pin, the pins have a grounded comb close to the lower roller, and the belt producing electronic point effect transfers more charge from the grounded comb to the belt. Inside the dome, another tip or a comb with many tips attached to the metal sphere gathers the charge from the belt due to the point effect, and the assembled charge will spread out across the whole spherical shell. Since the belt continuously carries charge from the voltage source to the dome, such an amount of charge can be accumulated on the spherical shell, which is only limited by the insulation of the device, the size of the dome, and the distance of the dome from other objects. The upper limit of the statics voltage produced by a van de Graaff generator may reach up to several million volts, and the device was used to accelerate particles up to reasonable high energies in nuclear physics. The last example for the application of the electric point effect is another electrostatic generator or influence machine invented by James Wimshurst, a British electrical engineer. The photo in the schematic figure illustrates its operation. The apparatus consists of two counter-rotating insulated discs which are covered with tinfoil sectors spaced at regular intervals. The rotating discs pass two pairs of metal neutralizer bars and their brushes set at right angles to each other, where the brushes are positioned near the surfaces of each discs. The brushes are denoted by the letter B in the figure. If a small amount of charge already resides on any of the sectors, then a process can start where each sector induces an equal and opposite charge on a passing sector on the other disc. The charges are collected by the two pairs of neutralizer bars and their brushes, applying the electric point effect, and allowing an exponential accumulation and separation of positive from negative charge at the output terminals T connected to the bars. At maximum output of the influence machine, the voltage at the terminals can range up to 10 to 4 volts, but the charge accumulated per second only reaches 10 to -5 coulombs. Then the current produced by the apparatus is usually 10 microamperes or less, and a Wimshurst machine is not suitable for being a current source. In the previous examples we examined how charged conductors can produce electric field, but in some cases we also studied the behavior of electrically neutral conductors in the vicinity of charged ones. If an electrically neutral conductor is placed in an electric field, then the positive charge carriers in the conductor are accelerated by the electric field strength and gain velocity in the direction of the field, whereas the negative charge carriers are pushed in the direction opposite to the field. The two ends of the conductor therefore attain opposite charges, producing an electric field inside the conductor, where the external and the internal electric fields have opposite directions. The displacement and the redistribution of the charge carriers will not stop until the electric field inside the conductor drops to zero and the electric field lines become perpendicular to the surface of the conductor. As a result, the electric field strength of the induced charges at the boundary surface of the conductor and the electric field strength producing the separation of charges cancel each other out inside the conductor. Outside the conductor, the field produced by the induced charges has a positive contribution to the external field at the two ends of the conductor, increasing the field strength there, whereas it has a negative contribution at the two sides of the conductor, decreasing the field strength there. These findings show us that the metal sphere used to measure the electric field strength in the previous experiments needs to be small enough and attain so small amount of charge that it has no significant effect on the electric field, and produces only a negligible modification in its field strength. For a conductor with a cavity, the induced charges have a distribution over the surface of the conductor in equilibrium such that the electric field vanishes within the cavity. In other words, the external electric field cannot penetrate the cavity because the conductor shields the cavity from the electric field. A metallic enclosure, For example, a fine metal mesh known as Faraday cage can provide a perfect electrostatic shield for the space enclosed by it. If a discharged electroscope is placed in a Faraday cage and a charged body producing a strong electric field is brought close to the cage, then the electroscope will not indicate any presence of the electric field. However, outside the cage, the foil leaves of the electroscope will move apart due to the separation of charge produced by the charged body. The electrostatic shielding effect of a metal box or a fine metal mesh is very useful for protecting sensitive devices from electromagnetic interference or any object from lightning strikes. Now we introduce a fundamental concept in electrostatic called capacitance. If we bring the electric charge Q to an isolated conductor far from other conductors, then the charge will be distributed over its surface such that the electric field strength E vanishes inside the conductor. The distribution of charge over the surface of a conductor is unique, and there is no other way to distribute the charge so that the field could be cancelled out within the conductor. Hence, if we bring the same amount of electric charge Q to the charged conductor, it will be distributed over the surface of the conductor in the same way as it was distributed in the first time. Otherwise, it would produce a non-zero electric field inside the conductor. In general, if different amounts of charges are brought on an insulated conductor, then the charges will always be distributed over the surface of the conductor in the same way. That is, the ratio of the surface charge densities at two arbitrary points on the surface of a conductor is always the same. As a result, we can assume that the electric potential of the conductor is proportional to the amount of electric charge distributed over its surface. Indeed, by increasing the amount of charge distributed over its surface, we can increase the electric field strength at every point in the vicinity of the conductor. Then the work done while a unit positive point charge is brought from infinity or the ground to the surface of the conductor, that is, the electric potential due to the charge distributed over the surface of the conductor, is increased as well. This finding can be formulated by stating that the amount of charge Q on the conductor must be directly proportional to the electric potential phi of the conductor, where the proportionality constant C is called the electric capacitance of the conductor. The capacitance C of a conductor is determined by the ratio of the amount of charge Q to the potential phi, and its value is equal to the amount of charge that the conductor needs to attain so that its potential can increase by unity. The larger of the capacity of a conductor, the greater the amount of charge can be stored in the conductor at a given potential. A conductor has a unit capacity if electric charge of 1 coulomb increases the potential of conductor through 1 volt. The unit of capacity is equal to 1 coulomb over 1 volt and called farad after the English physicist Michael Faraday, which and abbreviated by the letter F. Since 1 farad is a large value, normally its submultiples are in use, such as micro, nano and picofarad, that is 10 to minus 6, 9 and 12 farad. Capacity is independent from the charge and the voltage, but it depends on the shape and the size of the conductor. This statement can be demonstrated by the following simple experiment. We can bring a chain with a handle made of insulating material into contact with the top plate of an electroscope and charge the whole system formed by the electroscope and the chain. Then the golden leaves of the electroscope spread apart, indicating a given amount of charge distributed over its plate. However, if we lift the handle of the chain while the chain still remains in contact with the plate, then the distance between the end of the golden leaves decreases. Since the amount of charge stored in the system has not changed, we must conclude that the change in the geometrical properties of the system reduce the electric capacity of the system. By applying the definition of capacity, we can immediately derive the capacity of an isolated conducting sphere. We already determined the electric potential phi outside a charged conducting sphere, which is equal to 1 over 4 pi times epsilon naught, times the total charge Q of the sphere divided by its radius r. If we substitute this result into the definition, we can write the capacity C of an isolated conducting sphere as 4 pi times the vacuum permeability epsilon naught times its radius r. That is, the capacity of a sphere is proportional to its radius. For example, if we approximate Earth as a sphere of radius 6,370 kilometers, then this formula gives 700 microfarad, and only a sphere 1,500 times greater than Earth has a capacity of 1 farad. This example illustrates that a single conductor isolated from other objects has an extremely small capacitance. However, in practice there are many areas where devices are required that are capable to store a great amount of electric charge at low electric potential relative to the potentials of other objects in their vicinity. Such devices are called capacitors, and their operation based on the fact that the capacitance of a conductor can be increased by bringing other bodies close to them. For example, let us bring a metallic body into contact with the top plate of an electroscope and charge the system formed by the conductor and the electroscope. The gold leaves of the electroscope will spread apart, indicating the presence of electric charge. As we bring another grounded metallic body near the system, The gold leaves will decrease with the decreasing distance between the system and the grounded conductor. We can interpret this phenomenon by examining the distribution of the electric field between a charged conductor and the ground. If a grounded conductor is brought into the electric field due to the charged conductor, then the field causes a separation of charges in the grounded conductor. The charges induced in the grounded conductor modify the distribution of the electric field strength around the charged conductor, that is the distribution of the field lines emanating from the conductor. Let us compare the electric field between the charged conductor and the ground when the conductor is isolated and when the grounded conductor is in its vicinity. It can be demonstrated by measuring the electric field around the charged conductor that the field lines are denser over its surface close to the grounded conductor than between other parts of its surface and the ground. As a result, the work done while a unit positive charge is brought from the ground to the charged conductor will be less than the work done when the charged conductor is isolated or far from the grounded one. In other words, the electric potential of a charged conductor can be reduced by bringing a grounded conductor close to it. This is the reason why the combination of charged and grounded conductors has a greater capacitance than a charged conductor alone. Two conductors placed close to each other therefore form a capacitor, where the two conductors are called the plates of the capacitor. The capacitance of a capacitor is determined by the geometry and the arrangement of its plates. Furthermore, capacitance also depends on the medium between the two plates. In order to prevent external objects from having an effect on the capacitance of a capacitor or just minimize their effect, it is desirable to choose the shape of the plates of the capacitor and their arrangement with respect to each other such that the electric field due to the charges on the plates is concentrated between the plates. This condition can reasonably be satisfied by two parallel flat plates separated by a small distance known as parallel plate capacitor, two coaxial metallic cylinders called cylindrical capacitor, or two concentric metallic spheres known as spherical capacitor. If the electric field is concentrated inside a capacitor, then the electric field lines emanating from one of its plates must terminate on the other plate. As a result, the same amount of opposite electric charge is stored on each plate. One of the most important requirements for capacitors is the highest possible capacitance even with small size. As already mentioned, capacitance can be increased by modifying size, that is increasing the area of the plates, or modifying geometrical arrangement, that is decreasing the distance between the plates. We can also increase the capacitance of a capacitor if we place a medium between its plates that has a dielectric constant greater than 1. We note that there is a maximum limit of charging a capacitor determined by a maximum voltage between its plates. Besides capacitance, maximum voltage is also an important property of any capacitor that can be applied without causing electric breakdown of the dielectric material between its plates. For if this maximum or breakdown voltage is exceeded, then arcing will occur between the capacitor plates, and the dielectric material and the capacitor with it may become damaged. There are many different types of parallel plate, cylindrical and spherical capacitors applied in practice, such as block capacitors, variable capacitors, electrolytic capacitors, ceramic capacitors, organic dielectric capacitors, and so on. What we consider to be the very first capacitor was discovered by the German cleric Ewald Georg von Kleist and independently by the Dutch scientist Pieter von Maschenbroek of Leiden in 1745 and 1746, and the apparatus built by them is called the Leyden jar. In its earliest form it was a glass bottle that is partly filled with water, and the cork sealing the bottle was pierced with a wire running into the water. A brass rod with a brass sphere on its free end was also used instead of the wire. Here the glass served as the dielectric material of the capacitor. Later jars had sheets of metal foil wrapped around the inside and outside of the glass and no water. The outer sheet was connected to earth and the inner one had a suitable connection with the wire or brass rod by a metal chain. The jar could be charged by connecting the free end of the wire or the brass rod to a friction machine producing static electricity. In order to determine the capacitance of capacitors of different geometries, we use the definition of capacitance stating that if the electric potentials over the plates of a capacitor are given by phi1 and phi2, then the capacitance C of the capacitor is equal to the ratio of the amount of charge Q of the capacitor to the difference between the potentials phi1 and phi2. Here the charge plus Q is distributed over one of the plates of the capacitor and the charge minus Q is distributed over its other plate. The voltage V through the capacitor is defined by the difference between the potentials phi1 and phi2, and the capacitance C can also be written as the charge Q divided by the voltage V. Now we determine the capacitance of the three basic types of capacitors, starting with the parallel plate capacitor. Let us consider a parallel plate capacitor with two parallel plates of area A separated by distance d, where the capacitor has an electric charge plus Q on one plate and minus Q on the other one. If the distance d is much smaller than the sides of the plates, we can take the electric field to be nearly uniform between the plates by neglecting the bending of the field lines close to the sides of the plates. We already examined the uniform electric field between two parallel infinite plates due to the charge plus q and minus q uniformly distributed with the surface charge density sigma over the plates, and we found that its magnitude E is equal to the surface charge density sigma divided by the vacuum permittivity epsilon naught. Since the distribution of charge is uniform over the plates, the surface charge density sigma is equal to the amount of charge q on each plate divided by the area A of the plates. Then the electric charge q stored in the capacitor is given by epsilon naught times A times E. The potential difference phi1 minus phi2 between the two plates, that is the voltage V through the capacitor, is equal to the magnitude of the uniform electric field E between the two plates times the distance d between them. If we substitute these two equations into the general expression for the capacitance of capacitors, we can write the capacitance C of a parallel plate capacitor as epsilon naught times the ratio of the area A of the plates to the distance d between them. In other words, its capacitance is directly proportional to the area of the plates and inversely proportional to the distance between them. The formula obtained for the capacitance can also be verified by experiments measuring the charge Q of the capacitor and the voltage V through the capacitor. If the capacitance C of a parallel plate capacitor is already known with high accuracy, then we can determine the dielectric constant of vacuum from the geometry of the capacitor. The next type of capacitor for which we determine the capacitance is a cylindrical capacitor that consists of a conducting cylinder or wire of radius R1 surrounded by another coaxial cylindrical shell of radius R2, where L is the length of the cylinders. Let plus Q and minus Q be the charges on the inner and the outer cylinders, respectively. If the length L is much greater than the radii R1 and R2, then we can neglect the bending of the field lines at the two ends of the capacitor for the electric field between the cylinders produced by the charge distributed uniformly over their surfaces. As a result, the electric field depends only on the radius R measured from the axis of the cylinders and points radially outward from the axis. Let us choose a cylinder of the radius R as a Gaussian surface where the radius R is between the radii R1 and R2. Since no electric field line passes through the bases of the cylinders, Gauss' law states that the surface integral of the electric field E over the Gaussian surface given by the magnitude of the radial electric field E, times the area of the curved surface of the cylinder chosen as Gaussian surface, that is 2 pi times its radius R, times its length L, is equal to the total charge Q enclosed by the surface over epsilon naught. If we express the magnitude of the electric field E from the Gauss law, we obtain 1 over 2 pi times epsilon naught times the length L, times the charge Q over the radius R. The difference between the potentials phi1 and phi2 over the conducting cylinders, that is the voltage through the capacitor, is equal to the line integral of the electric field E along a path connecting the two cylinders. If we substitute the expression obtained for the magnitude of the radial electric field into the integral, we can write it as Q over 2 pi times epsilon naught times L, times the integral of 1 over R from R1 to R2 with respect to R. The integration gives the natural logarithm of the ratio of R2 to R1. By inserting this result into the capacitance formula, we can state that the capacitance C of a cylindrical conductor is equal to 2 pi times epsilon naught times its length L, over the natural logarithm of the ratio of the radius R2 to the radius R1 of its cylindrical surfaces. This formula also shows that the capacitance of a cylindrical capacitor depends on its geometry. The third type of capacitor for which we determine the capacitance is a spherical capacitor made up of a solid or hollow spherical conductor of radius R1, that is surrounded by another hollow concentric conducting sphere of radius R2. The charge plus Q can be brought to the inner sphere by applying an insulated thin wire passing through the outer sphere, and the charge minus Q can be brought to the outer sphere. Here we also assume that the charge is uniformly distributed over the surfaces of the spheres, and the electric field therefore depends only on the radius R measured from the center and points radially outward from the center. If we choose a spherical shell of radius R as Gaussian surface where R is between R1 and R2, then Gauss' law states that the surface integral of the electric field E over the Gaussian surface given by the magnitude of the radial electric field E, times the area of the sphere chosen as Gaussian surface, that is 4 pi times the square of its radius R, is equal to the total charge Q enclosed by the surface over epsilon naught. By expressing the magnitude of the electric field E from the Gauss law, we obtain 1 over 4 pi times epsilon naught, times the charge Q over the square of the radius R. The voltage through the capacitor, that is the difference between the potentials phi1 and phi2 over the conducting spheres, is equal to the line integral of the electric field E along a path connecting the two spheres. If we substitute the expression obtained for the magnitude of the radial electric field E into the integral, we can write the voltage as Q over 4 pi times epsilon naught, times the integral of 1 over r squared from r1 to r2 with respect to r. The definite integral is equal to minus 1 over r, evaluated at the upper and the lower limits of the integral. The reduction of the fractions on a common denominator gives r2 minus r1 over r1 times r2, which can be inserted into the capacitance formula. As a result, the capacitance C of a spherical conductor is equal to 4 pi times epsilon naught, times the radius r1 of its inner sphere times the radius r2 of its outer sphere divided by the difference between r2 and r1. If the radius r2 of the outer sphere tends to infinity, the power expansion of the ratio in the formula reduces to r1 and we regain the capacitance of a spherical conductor in the limit. In practice, it is important to combine capacitors of different capacitances such that their plates are connected or wired together in various ways. There are two basic combinations of capacitors where they are connected either in series or parallel. The figure shows two capacitors of capacitances C1 and C2 connected in series. If we connect a voltage source of V sub a B to the terminals A and B of the combination of the capacitors, then electrons will propagate through the conducting wires from the plate 1 of the first capacitor to the plate 2 of the second one, producing the charge plus Q on the plate 1 and minus Q on the plate 2. Since the plates 1' and 2' are not connected to the voltage source, no electric charge will leave these plates or arrive at them. However, the electric fields due to the charges accumulated on the plates 1 and 2 modify the distribution of charge on the plates 1' and 2'. For if we apply the principle of conservation of charge in the volume enclosing the connected plates 1' and 2', the electric fields induce the charge minus Q on the plate 1' and the charge plus Q on the plate 2'. Hence, each plate of the capacitors connected in series has the same amount of charge and the voltage V sub a C between the nodes A and C is equal to the voltage V1 through the first capacitor given by the ratio of the charge Q of the capacitor to the capacitance C1 of the capacitor. The voltage V sub CB between the nodes C and B is equal to the voltage V2 through the second capacitor given by the ratio of the charge Q of the capacitor to the capacitance C2 of the capacitor. Since the voltage V sub a B is equal to the sum of the voltages V sub a C and V sub CB, or the sum of the voltages V1 and V2 through the capacitors connected in series, it can be written as Q over C1 plus Q over C2. Here we express the ratio of the voltage V to the charge Q as the sum of 1 over C1 and 1 over C2. Now the question is what capacitance C a single capacitor must have if the difference of the potential V is applied between its two plates given by phi A minus phi B, then the charges plus Q and minus Q could be stored on its plates. In other words, we can ask when a capacitor of capacitance C is equivalent to two capacitors of capacitances C1 and C2 connected in series considering their net or equivalent capacitance. For the capacitance of the equivalent capacitor we know that the charge Q stored in the capacitor is given by the product of its capacitance C and the voltage V applied between its plates. We can divide this equation by Q and C and express V over Q as 1 over C. If we compare this expression with the result obtained for the two capacitors connected in series, then we see the condition of the equivalence, that is, 1 over the capacitance C of the equivalent capacitor must be equal to 1 over the capacitance C1 of the first capacitor, plus 1 over the capacitance C2 of the second one. Then the equivalent capacitance C is given by C1 times C2 divided by the sum of C1 and C2. We can generalize this result for n capacitors of capacitances C1, C2, Cn connected in series, and write that 1 over the capacitance C of the equivalent capacitor is equal to 1 over C1, plus 1 over C2, plus plus 1 over Cn, or the sum of 1 over Ci from I equals 1 to n. Then the capacitance C of the equivalent capacitor is given by 1 over the sum of the reciprocal of Ci from I equals 1 to n. In other words, the reciprocal of the equivalent capacitance of capacitors connected in series is equal to the sum of the reciprocal of the capacitances of the individual capacitors. It follows from these formulae that the net capacitance of capacitors connected in series is always less than the capacitance of any of the capacitors. If each capacitor connected in series has the same capacitance, then the equivalent capacitance is equal to the capacitance of the capacitors divided by their number. Now we determine the equivalent capacitance of two capacitors of capacitances C1 and C2 connected in parallel. As the figure shows, the difference between the potentials of the two plates of each capacitor is the same, but the amounts Q1 and Q2 of the electric charge stored on their plates are not necessarily equal to each other. We can write that the charge Q1 on the plates of the first capacitor is equal to the capacitance C1 of the capacitor times the voltage V applied between its plates. Similarly, the charge Q2 on the plates of the second capacitor is equal to the capacitance C2 of the capacitor times the voltage V applied between its plates. Then the total charge Q of the two capacitors connected in parallel is given by the sum of the charges Q1 and Q2 of the individual capacitors, which is equal to C1 times V, plus C2 times V, or the voltage V times the sum of the capacitances C1 and C2. This gives the equation stating that Q over V is equal to C1 plus C2. We can ask the question again: what is the capacitance C of a single capacitor equivalent to the capacitors of capacitances C1 and C2 connected in parallel, where the amount Q of charge given by the sum of the charges Q1 and Q2 is stored on its plates if the voltage V is applied between them. It holds for the capacitor equivalent to the two capacitors connected in parallel that its charge Q divided by the voltage V applied between its plates is equal to the capacitance C of the capacitor. By comparing the two equations with each other's, we conclude that the capacitance C is equal to the sum of the capacitances C1 and C2. Generally, if n capacitors of capacitances C1, C2, Cn are connected in parallel, then the capacitance C of the capacitor equivalent to them is given by C1, plus C2, plus plus Cn, or the sum of Ci from I equals 1 to n. In other words, the equivalent capacitance of capacitors connected in parallel is given by the sum of the capacitances of the individual capacitors. As opposed to the case of capacitors connected in serial, the equivalent capacitance of capacitors connected in parallel is always greater than the capacitances of the individual capacitors. By connecting more than two capacitors to each other, we produce more complex combinations, and these combinations can be reduced to the two basic forms in some cases: capacitors connected in series or parallel. As a result, some combinations of capacitors can be transformed into simpler forms by applying the equivalence transformation of capacitors. For example, in the figure, the capacitor of capacitance C1 is connected in series with capacitors of capacitance C2, C3 and C4 connected in parallel. The capacitors connected in parallel have the equivalent capacitance C' given by the sum of C2, C3 and C4, and we can replace their combination with their equivalent capacitor of capacitance C'. Since we have obtained the combination of two capacitors in series, the equivalent or total capacitance C of the whole system is equal to C1 times C' divided by the sum of C1 and C'. In the next example, we show a more complicated combination of capacitors which can also be simplified by applying the equivalence transformation of capacitors connected in series or parallel. We can perform this transformation in several different ways, and here we start with the capacitors of capacitances C1 and C2 connected in series and the capacitors of capacitances C5 and C6 connected in parallel. In the first step, we introduce the equivalent capacitors of capacitance C given by C1 times C2 divided by the sum of C1 and C2 for the capacitors connected in series, and the equivalent capacitor of capacitance CB given by the sum of C5 and C6 for the capacitors connected in parallel. In the second step, we apply the equivalence transformation for the capacitors of capacitances CA and C3 connected in parallel, and the capacitors of capacitances C4 and CB connected in series by replacing them with the equivalent capacitor of capacitance CD given by CA plus C3, and the equivalent capacitor of capacitance CE given by CB times C4 over the sum of CB and C4. Now we have the capacitors of capacitances CD and CE connected in parallel, and we can reduce their combination into the capacitor of capacitance C given by the sum of CD and CE. As a result, we can replace the original combination of 6 capacitors with a single equivalent capacitor of the total capacitance C when examining how much charge can be stored in the system for a given voltage V applied on its terminals. The equivalent capacitance C of the whole system is a unique expression of the individual capacitances depending on the topology of their combination, that is, the way how they are connected to each other. However, some combinations of capacitors, for example the one seen in the figure, cannot be reduced to the problem of capacitors connected in serial or parallel. Although the equations describing the charges of the capacitors and the voltages through them can be solved for such a combination, it is simpler to apply the so-called star-delta transformation for it, which we will discuss later. The concept of capacitance described above can be applied in the cases involving only two plates or electrodes over which equal but opposite electric charges are distributed. In general, if a system consists of charged conductors or electrodes, then the electric potential of every conductor depends on the charges distributed over the surfaces of all the conductors. As an illustration of the general case, let us consider the conductors or electrodes 1, 2 and 3 with charges Q1, Q2 and Q3, which have the electric potentials Phi1, Phi2 and Phi3 with respect to the earth or ground denoted by 0. Then the system of conductors consists of the electrodes 1, 2 and 3 together with the ground considered as the electrode 0 of 0 electric potential. By supposing that the properties of the media around the electrodes are independent from the electric field due to the charge stored in the system, we can express the potential of each electrode as the superposition of the individual fields due to the charges distributed over the surfaces of the individual electrodes, since Gauss' law is linear in the electric potential phi of the field. As a result, the potential phi I on the electrode I can be written as a linear function of all the charges, that is the sum of the coefficients of potential A sub ij, times the charge qj on the electrode j from j equals 1 to the number n of the electrodes. This equation can be interpreted as a vector equation, where the vector of the potentials of the conductors is equal to the product of a matrix with the elements given by the coefficients of potential and the vector of the charges on the conductors. Then the potential phi I of each electrode in the example where I is equal to 1, 2 and 3 is given by a matrix equation, where the 9 coefficients of potential form a 3 times 3 matrix. Each diagonal element of this matrix represents the contribution of the charge on a given conductor to its own potential. The diagonal elements therefore describe the self-capacitance of the conductors. The off-diagonal elements A sub ij of the coefficient matrix represent the contribution of the charge on the electrode I to the potential on the electrode j, and are known as mutual potential coefficients. The matrix A sub ij is a symmetric matrix, that is A sub ij is equal to A sub ji for all I and j from 1 to n. This property immediately follows from the reciprocation theorem stating that the sum of the charge qi on the conductor I times the potential phi prime I of the same conductor from I equal t to n, is equal to the sum of the charge q prime I on the conductor I times the potential phi I of the same conductor from I equals 1 to n. This theorem will be discussed in details when we study energy in electrostatic field. Here the potentials phi I of the conductors are generated by the charges qi distributed over their surfaces, and the potentials phi prime I of the same conductors are generated by the charges q prime I on them. If we insert the expressions of the potentials phi I in the left-hand side into the theorem, then we can see that the matrix of the coefficients of potential must be symmetric. Usually, the inverse problem can also be discussed where the potentials of the electrodes are known. By inverting the matrix of the coefficients of potential, we can write the charge qi on the electrode I as the sum of the coefficient A over minus 1 sub ij times the potential phi j. That is, the vector of the charges on the electrodes is equal to the product of the inverse matrix of A and the vector of the potentials of the electrodes, as seen in the example. Here the elements of the inverse matrix of A have the unit of capacitance and are called partial capacitances relative to the ground. Since partial capacitances can be negative, an equivalent scheme is used where each pair of conductors is replaced by capacitors with given capacitances, and the amount of charges on the conductors are expressed by the differences between the potentials of the different electrodes including the ground. That is, the charge qi of the electrode I from I equals 1 to n is given by the sum of the coefficients C sub ij, times the difference between the potentials phi I and phi j of the electrodes I and j from j equals 0 to n. Here the potential phi 0 of the earth is equal to 0. And the relationship between the inverse matrix of the coefficients of potential and the coefficient C sub ij is the following. The diagonal component of the inverse matrix in the ith row and column is given by the sum of C sub ij from j1 equals 1 to n, whereas the off-diagonal elements of the inverse matrix with indices I and j are equal to minus the coefficients C sub ij. In the example, the voltage between the electrodes 1 and 2 is equal to the difference between the potentials phi 1 and phi 2. Similarly, the voltages between the electrodes 1 and 3 and between the electrodes 2 and 3 are given by the difference between phi 1 and phi 3 and the difference between phi 2 and phi 3, respectively. In the figure we indicated both directions between the conductors which can be applied to determine the voltages. The coefficients C sub ij are always positive and can be interpreted as capacitances of the equivalent scheme forming the capacitance matrix of the system of conductors. Again, the diagonal elements of the capacitance matrix correspond to the contribution to the charge qi on the conductor I caused by its own potential phi I, providing the self-capacitance of the conductor. The coefficients C sub ij where I and j are different represent the contribution to the charge on conductor I caused by the potential difference between this conductor and the conductor j. This contribution is equivalent to the capacitance of the capacitor formed by the electrodes I and j, and these coefficients are called partial capacitances. In the example we have three equations expressing the charges Q1, Q2 and Q3 in the terms of the potential differences which we can interpret as follows. The charge Q1 is decomposed into three parts in the first equation, the amount proportional to the potential phi 1 with the self-capacitance C sub 1 0 of the conductor 1, the amount proportional to the voltage phi1 minus phi2 between the conductors 1 and 2 with the partial capacitance C sub 1 to the of these conductors, and the amount proportional to the voltage phi1 minus phi3 between the conductors 1 and 3 with the partial capacitance C sub 1 3 of these conductors. We can give the analogous interpretation of the two other equations as well, which shows that each electrode has one self-capacitance and two partial capacitances. For a system of n electrodes, each electrode has one self-capacitance and n-1 partial capacitances. Now we will discuss Green's reciprocation theorem, which we used in a special case to show the symmetry of the matrix of coefficients of potential, and demonstrate that the theorem is closely related to the energy of a system of conductors. The general form of Green's reciprocation theorem is the following. If phi is the potential due to a volume charge density ρ within a volume V and a surface charge density sigma on the conducting surface S bounding the volume V, while phi prime is the potential due to another charge distribution described by ρ prime and sigma prime, then the volume integral of ρ times phi prime over the volume V plus the surface integral of sigma times phi prime over the surface S, is equal to the volume integral of ρ prime times phi over the volume V plus the surface integral of sigma prime times phi over the surface S. We already demonstrated that the electric field within a cavity in a charged conductor vanishes provided no charge distributed over an insulator or charged conducting material insulated from the conductor is placed into the cavity. Since the volume charge densities ρ and ρ prime in the theorem represent such distributions of charges within the volume V enclosed by the charged conductive surface S, we can talk about a non-zero electric field within the volume V described by the non-constant potentials phi and phi prime. In order to prove the theorem, we apply Green's second identity stating that the volume integral of the difference between phi times the Laplacian of phi prime and phi prime times the Laplacian of phi over the volume V, is equal to the surface integral of the difference between phi times the directional derivative of phi prime in the direction of the outward pointing surface normal n to the surface S of the volume V, and phi prime times the directional derivative of phi in the direction of the surface normal n. Here the normal n points away from the volume V that is into the conductor, since the volume V is the non-conducting region bounded by the conducting surface or surfaces S. The Laplacian of the potential phi in the volume integral is equal to the divergence of the gradient of the potential, where the negative gradient of the potential is equal to the electric field strength E of the electrostatic field described by the potential phi. Then we can use Gauss' law stating that the divergence of the electric field E is equal to the electric charge density ρ producing the field over the vacuum permittivity epsilon naught. As a result, we have Poisson's equation stating that the Laplacian of the electric potential phi is equal to minus the electric charge density ρ over epsilon naught. Similarly, we can write that the Laplacian of the potential phi prime is equal to minus the electric charge density ρ prime over epsilon naught. If we substitute the two Poisson's equations into the Laplacians in the left-hand side of the identity and multiply the result by epsilon naught, we can write that minus the volume integral of the difference between phi times ρ prime and phi prime times ρ over the volume V, is equal to the surface integral of the difference between epsilon naught times phi times the directional derivative of phi prime, and epsilon naught times phi prime times the directional derivative of phi over the surface S. We already demonstrated that the electric field is perpendicular to the surface of a charged conductor and its magnitude is given by the ratio of the surface charge density sigma to epsilon naught. Since the surface of a conductor is an equipotential surface, the electric field E given by the negative gradient of the potential phi is equal to the directional derivative of the potential in the direction of the outward pointing surface normal n of the conductor, and we can express the surface charge density sigma as minus epsilon naught times the directional derivative of the potential phi in the direction of the surface normal n over the surface S. Here the normal n is directed outward from the volume of the conductor, while the normal n in Green's second identity points inward. If we reverse the direction of the normal, then sigma is equal to the directional derivative of phi in the direction of the surface normal n pointing inward the volume of the conductor, and we can write the same equation for sigma prime and phi prime. By substituting these two expressions into Green's second identity, we obtain the equation stating that minus the volume integral of the difference between phi times ρ prime and phi prime times ρ over the volume V, is equal to the surface integral of the difference between phi times sigma prime and phi prime times sigma over the surface S. Now we can expand the brackets in the integrals and shuffle the second terms in both sides, which gives Green's reciprocation theorem. After having proven the theorem, we explain how it is related to the potential energy of a system of charged conductors. First, we note that the electrostatic potential energy U of a volume charge distribution ρ producing the electrostatic potential phi, is given by 1 over 2 times the volume integral of the product of the electric charge density ρ and the potential phi over the volume V enclosing the non-vanishing region of the charge distribution. For an electric charge distribution sigma over a surface S, the volume integral providing the potential energy U can be reduced to the surface integral of sigma times phi over the surface S. By taking a look on the volume and surface integrals in Green's reciprocation theorem and comparing them with the two integrals of the electrostatic potential energy of a charged system, we can interpret the reciprocation theorem as follows. If the charge densities ρ and sigma were at rest in the potential phi prime, then their total potential energy would be the same as that of the charge densities ρ prime and sigma prime held at rest in the potential phi. In order to illustrate this statement, let us derive the version of reciprocation theorem for systems of point charges from the definition of the electrostatic energy of such systems. We already demonstrated that the potential energy U of a system of point charges Q1, Q2, ellipsis, Qn at the positions R1, R2, ellipsis Rn is equal to 1 over 2 times the sum of Qi times phi I from I equals 1 to n, where the potentials phi I are given by the sum of 1 over 4 pi times epsilon naught, times the charge Qi over the distance R sub ij from j equals 1 to n excluding I. Here R sub ij denotes the distance between the charges Qi and Qj. We also consider another system of point charges Q' I at the same positions producing the potentials phi prime I from I equals 1 to n, where Qi is replaced by Q' I in the formulae of the potentials. Now we start with the computation of the product of the charge Q1 and the potential phi prime 1. By inserting the explicit expression of the potential and expanding the sum in it, we obtain 0 for j equals 1, plus 1 over 4 pi epsilon naught, times Q1 times Q' 2 over R sub 1 2, plus 1 over 4 pi epsilon naught, times Q1 times Q' 3 over R sub 1 3, plus ellipsis, plus 1 over 4 pi epsilon naught, times Q1 times Q' n over R sub 1 n. We also expand the product of the charge Q2 and the potential phi prime 2, which gives another sum with the vanishing second term in the right-hand side. If we multiply the charge Q3 by the potential phi prime 3, we obtain a third sum where the third term is 0 in the right-hand side. We can continue this procedure till the product of the charge Qn and the potential phi n, which gives the last sum with the vanishing last term. Now we have an equations where can add the terms in each column separately. If we add the left-hand side of these equations, then we obtain the sum of Qi times phi prime I from I equals 1 to n. The sum of the terms forming the first column in the right-hand side gives Q'1 times the sum of 1 over 4 pi times epsilon naught, times Qj over R sub 1j from j equals 1 to n excluding 1. By summing up the terms in the second column, we have Q'2 times the sum of 1 over 4 pi times epsilon naught, times Qj over R sub 2j from j equals 1 to n excluding 2. Similarly, if we add the terms in the third column, we obtain Q'3 times the sum of 1 over 4 pi times epsilon naught, times Qj over R sub 3j from j equals 1 to n excluding 3. We can continue this procedure up to the last column, where the sum is equal to Q'n times the sum of 1 over 4 pi times epsilon naught, times Qj over R sub nj from j equals 1 to n excluding n. Now we can add all the sums obtained in the right-hand side, which gives the sum of Q'I times phi I from I equals 1 to n. As a result, we have a special case of Green's reciprocation theorem for the systems of electric charges Qi and Q'I at the same positions producing the potentials phi I and phi prime I from I equals 1 to n, which states that the sum of Qi times phi prime I from I equals 1 to n, is equal to the sum of Q'I times phi I from I equals 1 to n. If we compare this result with the potential energy for a system of charges, then we can immediately give the same interpretation of the special case of the theorem as in the general case. That is, if the system of charges Qi were at rest in the potential phi prime I, then their total energy would be the same as that of the system of charges Q'I held at rest in the potential phi I, where I runs from 1 to n. We use this special form of the theorem to prove that the matrix of coefficients of potential is symmetric. However, we need to clarify how to apply the theorem proven for a space enclosed by a conducting surface to a set of conductors without any boundary surface around them. When we studied the capacitance of a system of conductors, we considered an arbitrary arrangement of charged conductors or electrodes, and determined the relationship between their potentials and the charges distributed over their surfaces. Although the Earth was also the part of the system as an electrode 0 of 0 potential, the conductors 1, 2 and so on were not enclosed by another conducting surface in the general case. However, even in the general case, the finite amount of charges Q1, Q2 and so on distributed over the surfaces of the conductors 1, 2 and so on are localized in space, and the electric field produced by these charges vanishes at infinity. Therefore, any imaginary equipotential surface S0 of zero charge and zero potential at infinity joined with the earth or the electrode 0 can be considered as an uncharged conducting surface that encloses the system of charged conductors. The union S of the conductive surface S0 and the boundary surfaces of the electrodes 1, 2, and so on denoted by S1, S2 and so on forms a boundary of the volume V enclosing the region of the system of electrodes but excluding the electrodes themselves. As a result, this problem is equivalent to the one described by Green's reciprocation theorem, where the surface charge density sigma describing the distribution of charge over the surface S is given by the different surface charge densities sigma 1, sigma 2 and so on over the patches S1, S2 and so on of the boundary S. If there are no space charges in some dielectric medium between the conductors within the volume V, then the volume charge density ρ vanishes. These statements hold for the primed versions of sigma and ρ as well. For vanishing ρ and ρ prime, the reciprocation theorem reduces to the surface integrals over the boundary surface S. We can break up the surface S into the patches S0, S1, S2 and so on in the surface integrals, where each patch represents an equipotential surface. Then the constant potentials phi and phi prime can be factored out from the surface integrals over the patches, leaving only the surface charge densities sigma and sigma prime in the integrals. Since the integrals give the total charge Qi over the patch Si, that is the surface of the conductor I, we regain the reciprocation theorem. For the total charges Q1, Q2, ellipsis Qn distributed over the surfaces of the conductors 1, 2, ellipsis, n producing the potentials phi 1, phi 2, ellipsis, phi n of the conductors, the sum of Qi times phi prime I from I equals 1 to n is given by the sum of Q prime I times phi I from I equals 1 to n. Here the charges Q prime I distributed over the surface of the conductors I produce the potentials phi prime I from I equals 1 to n. This is the form of the theorem applied to prove that the matrix of coefficients of potential, and therefore the capacitance matrix of the system of conductors is symmetric. This form also follows from the expression obtained for a system of point charges if we assume that the point charges are distributed over the surfaces of conductors. Since these surfaces are equipotential surfaces, the sums in both the sides of the expression can be written as the sums of the constant potential of a given conductor times the sum of the point charges on the surface of that conductor, that is the total charge of the conductor. An immediate consequence of the theorem is the following. If the charge Q1 is equal to the charge Q'2 while all the other charges Qi and Qi' vanish, then the theorem can be reduced to the equation stating that the potential phi'1 is equal to the potential phi2. Let Q denote the equal charges Q1 and Q'2, and consider a situation where we charge only one electrode in the system by bringing the charge Q to the electrode 1 while all the other conductors remain uncharged. Then the electric field produced by this charge will induces charges on the surfaces of the uncharged conductors, which raises their electric potential. If we bring the charge Q to the electrode 2 while all the other conductors are uncharged, then this charge also raises the potential of the uncharged conductors. The consequence of the theorem states that the potential to which the uncharged conductor 1 is raised by putting the charge Q on the conductor 2 is the same as that to the conductor 2, when uncharged, will be raised by putting the charge Q on the conductor 1. Another consequence of the theorem is related to the superposition of electric fields. If we add the sum of Qi times phi I to the equation in the theorem, then we obtain an equation stating that the sum of Qi times the sum of phi prime I and phi I is equal to the sum of Q prime I and Q prime I times phi I. By comparing the result with the equation in the theorem, we can see that if the charges Q1, Q2, ellipsis, Qn produce the potentials phi 1, phi 2, ellipsis, phi n, then the charges Q1 plus Q'1, Q2 plus Q'2, ellipsis, Qn plus Q'n give the potentials phi 1 plus phi prime 1, phi 2 plus phi prime 2, ellipsis, phi n plus phi prime n. This consequence shows that many problems in electrostatic can be solved by superimposing of the solutions of known problems. We have already determined the energy of a system of electric charges which is applied when we ask how much energy a given system of conductors has. We obtained this energy by calculating the work required to produce a state in which the conductors have given charges and potentials. As a result, the electric energy of a system could be expressed in the terms of charges and potentials. Now we express the electric energy of a system of conductors in the terms of capacitances and potentials or charges, and we show that it can be done by applying the quantities describing the electric field. We determine the energy of a charged capacitor given by the work required to bring charge to its plates. If the conductors A and B are the plates of the capacitor of capacitance C, then the energy of the capacitor can be calculated as follows. At a given instance of time t, let q' and minus q' be the charges on the plates A and B, respectively. Then the voltage V between the conductors is equal to the charge q' over the capacitance C, where q' and therefore the voltage V depends on the time t. If we bring an infinitesimal positive charge dq' from the plate B to the plate A, then the work dW done against the electrostatic force between the plates is given by the voltage V, that is the difference of the potential between the two plates, times dq'. This work can be expressed as q' over C times dq'. The work W required to bring the charge Q to the initially uncharged capacitor is the sum of such infinitesimal works, that is the integral of dW, or the integral of Q' divided by C from 0 to Q with respect to Q'. Since the capacitance C is constant, the primitive function of the integral is equal to the square of Q' over 2 times C, and the work W is given by 1 over 2 times the square of the charge Q divided by the capacitance C. If the capacitor is gradually charged, in each step a given amount charge is brought to its plates, producing an electric field between them, but no other change occurs. As a result, we can assume that the work required to charge the capacitor is completely converted into the energy of the charge Q. Then the energy U of a capacitor storing the charge Q is equal to 1 over 2 times the ratio of the charge Q squared to the capacitance C of the capacitor, or 1 over 2 times the capacitance C times the square of the voltage V between the plates of the capacitor. This result holds for any capacitor independently of its structure. It is also valid for a single conductor provided the voltage V is equal to the electric potential of the conductor with respect to a point at infinity. The inverse process of the gradual charging of a capacitor is its gradual discharging, where the capacitor can do work on any physical system residing its electric field. The experiment shown in the figure illustrates how work is done during the discharge of a capacitor. A small metal sphere suspended from a string made of silk will attain positive charge when it is brought into contact with the plate A of the capacitor. As a result, the ball is repelled from the plate A and attracted to the plate B due to the electrostatic forces between like and opposite charges. When the ball gets into contact with the plate B, it loses its positive charge and attains -1. Then the electrostatic forces drive the ball from the plate B to the plate A, where it reduces the positive charge of the plate A, and so on. The gradual decrease in the charge of the capacitor or in the voltage between its plates can be measured by an electroscope connected to the plate A of the capacitor. In order to provide the general expression for the energy density of an electrostatic field, we determine the energy of the electrostatic field and its density between the plates of a capacitor. We have seen that the energy U of such a field is given by 1 over 2 times the capacitance C of the capacitor, times the square of the voltage V sub C between its plates. For parallel plate capacitors producing a uniform electric field E between their plates, the voltage V sub C defined by the difference in the potential phi between the plates is equal to the magnitude of the electric field E times the distance d between the plates. We also demonstrated that the capacitance C of a parallel plate capacitor is given by the dielectric constant of vacuum epsilon naught, times the area A of the plates of the capacitor over the distance d between the plates. If we substitute these equations into the expression of the energy U, then we obtain 1 over 2 times epsilon naught times the square of the magnitude of the electric field E, times the area A times the distance d. Here the volume V between the plates is given by the area A of the plates times the distance d between them, and the energy U of the electric field is equal to 1 over 2 times epsilon naught, times the square of the magnitude of the electric field E times the volume V. We can interpret this result as the fact that the energy U is not distributed over the plates of the capacitor, but it is stored in the volume V between the plates, where the electrostatic force field is produced. Since this field is uniform for parallel plate capacitors, the energy per unit volume, that is the energy density denoted by lowercase u, is equal to 1 over the vacuum permittivity epsilon naught, times the square of the magnitude of the electric field strength E. Although we derive this result for parallel plate capacitors, it holds in the general case as well. In other words, the energy density of an electrostatic field at any point of the field is directly proportional to the square of the electric field strength at the given point. For example, the magnitude of the electric field E due to a charged sphere at the distance r from its center is given by 1 over 4 pi times epsilon naught, times the total charge q of the sphere divided by the distance r squared. Then the energy density lowercase u of the electrostatic field due to the charged sphere is equal to 1 over 32 pi squared times epsilon naught squared, times q squared over the distance r raised to 4. That is, the energy density of a charged sphere is inversely proportional to the fourth power of the distance from its center. The same relationship holds for the electric field due to a point charge as well. For non-uniform electric fields, the general expression of the energy density u is defined by the derivative of the energy U with respect to the volume V. Then the infinitesimal amount of energy du within the infinitesimal volume element dV is equal to the energy density u times the volume element dV. By inserting the result obtained for the energy density into this equation, we can write du as 1 over 2 times epsilon naught times E squared times dV. The total energy of the electrostatic field is equal to the integral of the infinitesimal quantity of du, or the volume integral of the energy density u. And as the formula shows, the general expression of the energy U of a non-uniform electrostatic field is given by 1 over 2 times the vacuum permittivity epsilon naught, times the volume integral of the square of the electrostatic field strength E. We note that this formula describes the energy of a capacitor in the terms of electric field strength produced in the space between the plates of the capacitor, as opposed to the expression written in the terms of the charge distributed over the plates, the capacitance of the capacitor or the difference in the potential between the plates. From the viewpoint of electrostatics, we have to ask the question where energy is localized, or what is the medium of energy? Either electric charge or electrostatic field? In electrostatics, where we study static electric fields due to charges at rest, this question cannot be answered, since static electric fields and the charges at rest producing them do not exist in separation from each other. It is however not the case for time-evolving electric fields, which can exist independently from the charges producing them and propagate in the form of electromagnetic waves. Experiments already demonstrated that electromagnetic waves can transport energy, and the medium of energy is the electromagnetic field. Now we determine the energy of a system of charged conductors based on the general formula expressing the energy of an electrostatic field in the terms of the field variables, and derive another formula depending on the capacitances of the conductors in the system. We consider a system of charged conductors 1, 2 and so on having the charges Q1, Q2 and so on, where the system is localized and the electric field due to the charges vanishes at infinity. Then the electrostatic energy U of the system is given by 1 over 2 times epsilon naught, times the volume integral of the square of the electric field strength E. Here E squared is simply equal to the dot product of the electric field strength E, and we can write any of the factors in the dot product as the negative gradient of the electric potential phi. If we use the product rule for derivatives, then we can split the volume integral into the integral of the divergence of the product of phi and E, and the integral of the divergence of E times phi. Since there are no space charges in the volume over which these expressions are integrated, that is, the volume charge density ρ is 0, Gauss's law tells us that the electric field is divergence-free and the second integral vanishes. In the first term we can apply Gauss's theorem, and write the volume integral of the divergence of phi times E as the surface integral of phi times E over the surface boundary S of the volume V enclosing the electrostatic field. The dot product of phi times E and the surface element S in the surface integral indicates that only the projection of the electric field onto the surface normal gives a contribution to the integral. As the figure shows, the volume V enclosing the localized electric field due to the system of charged conductors has the boundary S, that is the union of the surface S0 and the boundaries S1, S2 and so on of the electrodes 1, 2 and so on. Here the surface S0 is a surface of zero potential, that is the combination of the Earth considered as the electrode 0 and an imaginary surface at infinity where the potential of the localized electric field vanishes. Then we can split the surface integral into the sum of integrals over the charged boundaries of the n conductors in the system, where we omitted the integral over the surface S0 of zero potential. Since the electric field E is always perpendicular to the boundary of a conductor in its vicinity, we use the component of E that is normal to the surface in the integral. The change in the sign of the integral indicates that E sub n points outward from the surfaces of the conductors, which is opposite to the outward normal to the boundary of the volume V of the integration. We can also factor out the constant potential phi from the integrals over the boundaries of the conductors, which are equipotential surfaces. The normal component of the electric field is just equal to the negative gradient of the potential in the normal direction, that is the directional derivative of phi in the direction of the surface normal n. The positive sign of the directional derivative is the consequence of the fact that the normal n points outward from the volume V and inward to the conductor, that is in the direction of the increasing electric potential outside the conductor. We already saw that epsilon naught times the directional derivative of the potential in the normal direction n is equal to the surface charge density sigma over the surface of the conductor. Again, the missing negative sign in the front of the derivative indicates that the normal used here points outward from the volume V and inward to the conductor. By inserting this expression into the sum of integrals, we obtain the surface integrals of the surface charge densities sigma I of the charge distributed over the boundary Si of the conductor I for I running from 1 to n. These surface integrals then give the total charge distributed over the surface of each conductor, and the energy of the electrostatic field due to the charges distributed over the surfaces of conductors, is given by 1 over 2 times the sum of the potential phi I of the conductor I, times the charge qi of the conductor I from I equals 1 to n. We already established that the potentials phi I can be expressed as functions of coefficients of potential and charge, or in the inverse problem the charges qi can be written as functions of partial capacitances and potentials. As a result, the energy U has a quadratic form, that is U is equal to 1 over 2 times the sum of the coefficient of potential A sub ij, times the charge qi, times the charge qj from I and j equal 1 to n, or 1 over 2 times the sum of the partial capacitance given by the inverse of A sub ij, times the potential phi I, times the potential phi j from I and j equal 1 to n. When the electrostatic energy is expressed as a quadratic form of the potentials, partial capacitances are used to define the elements of the Maxwell capacitance matrix. Then the electrostatic energy U of n charged conductors is given by 1 over 2 times the sum of the element ij of the Maxwell capacitance matrix Cm, times the potential phi I of the conductor I, times the potential phi j of the conductor j from I and j equal 1 to n. We already introduced the capacitance matrix of a system of conductors and expressed the partial capacitances of the system as functions of the elements of the capacitance matrix. If we replace the partial capacitances by the elements of the Maxwell capacitance matrix, then we can write the diagonal elements of the Maxwell capacitance matrix Cm for the index I as the sum of the elements ij of the capacitance matrix C from j equals 1 to n. We also mentioned that the elements of the capacitance matrix are positive. Hence the diagonal elements of the Maxwell capacitance matrix must be positive. The off-diagonal elements of the Maxwell capacitance matrix Cm are equal to minus the corresponding elements of the capacitance matrix C. Since the later ones are positive, the off-diagonal elements of the Maxwell capacitance matrix are negative. In fact, these properties follow from the positivity of electrostatic energy. We can see that the energy U given by the volume integral of the square of the magnitude of the electric field is positive definite, and the quadratic forms of the electrostatic energy must be positive definite as well. Then the signs of the capacitance matrices can be justified by solving Laplace's equation over the volume enclosing the field and determine its positivity in the whole space. A less formal justification can be given by supposing that all conductors except the conductor I are grounded. In the figure the conductor I is the first electrode. Then the electric charges of all conductors are proportional to the potential of the conductor I, where the constant of proportionality for the conductor J is the element ij of the Maxwell capacitance matrix. Since the potential and the electric charge of the conductor I have the same sign, the diagonal elements of the Maxwell capacitance matrix must be positive, which holds for an arbitrary index I. In presence of the isolated conductor I with charge there will appear induced charges at surfaces of all remaining grounded conductors such that their sign will be opposed to the charge of the conductor I. In other words, the sign of induced charge is opposed to the sign of inducing potential. It means that the off-diagonal elements of the Maxwell capacitance matrix must be negative, that is, the off-diagonal elements of the capacitance matrix must be positive. After having derived the expression describing the potential energy of electrodes, we determine electric forces on charged conductors. We calculate the infinitesimal force exerted on an infinitesimal area element ds of the surface S of a charged conductor, where we suppose that the conductor has a positive net charge. The surface area element ds of the charged conductor is located in an electric field E double prime due to the charge distributed over other parts of the surface S of the conductor. As a result, the direction of the field close to the area element is the same in its both sides pointing outward from the conductor. By definition, the force acting on a given amount of charge located in an electrostatic field is the product of the charge and the electric field strength. Then the force dF exerted on the surface area element ds containing the charge given by the surface charge density sigma times ds can be written as sigma times ds, times the magnitude of the electric field E double prime. We have already shown that the electric field E due to the total charge distributed over the surface S of a conductor vanishes within the conductor and it is perpendicular to the surface close to the conductor. Its magnitude at the surface is given by the surface charge density sigma over epsilon naught. The charge distributed over the surface element ds also produces an electric field E prime, pointing away from the charged surface. As the figure shows, the electric field E double prime is the same at two corresponding points in the opposite sides of the surface area element ds, whereas the electric field E prime points in opposite directions and only its magnitude is the same in the opposite sides of the area element. Then the superposition of the fields E prime and E double prime outside the conductor is the following. The net electric field E is equal to the sum of the magnitudes of the fields E prime and E double prime, which must give sigma over epsilon naught. Within the conductor they have opposite directions and their superposition gives the difference between their magnitudes, where the net electric field E vanishes. We immediately conclude from the second equation that the magnitudes of the field E' and the field E" are equal. Then the first equation tells us that their magnitudes are given by sigma over 2 times epsilon naught. As a result, the electrostatic force dF acting on the infinitesimal surface area element ds given by E" times sigma times ds, is equal to sigma squared over 2 times epsilon naught, times ds. If we substitute the relationship between the surface charge density and the field strength into the right-hand side, then we obtain 1 over 2 times E times sigma times ds, or 1 over 2 times epsilon naught times the square of the electric field strength E, times ds. The result shows that the force acting on a unit surface area of a charged conductor, that is the surface density of the force given by the derivative of the force F with respect to the surface area S, is equal to the square of the surface charge density sigma divided by 2 times the vacuum permittivity epsilon naught, or 1 over 2 times the magnitude of the electric field E due to the surface charge, times the surface charge density sigma. This expression can also be written as 1 over 2 times the vacuum permittivity epsilon naught times the square of the magnitude of the electric field E, where we can recognize the expression obtained for the energy density U of an electrostatic field. Then we find that the surface density of the force exerted on a given surface area element is equal to the volume density of the electrostatic energy at the surface area element. We can also deduce the same result for the force on a charged conductor by applying the principle of virtual work. We determine the virtual work done while an infinitesimal volume element of the conductor at its surface is displaced in the direction normal to the surface. The cylindrical volume element has the base of the surface area S and its height is given by the virtual displacement delta x along the surface normal. The virtual work delta W done on the charged volume element when it is displaced by the force F on the surface of the conductor is equal to the magnitude of the force F times the displacement delta x, since the electric field representing the force is parallel with the displacement at the surface of the conductor. As the result of the virtual displacement, the electric field is reduced to zero in the space occupied by the displaced volume element of the conductor with vanishing electric field inside, but there is no other change in the field outside the volume element, at least to the first order. Then we can assume that the change in the energy of the electric field in the space occupied by the displaced volume element is completely converted into the virtual work done on the volume element. The infinitesimal change du in the energy can be written as the energy density lowercase u of the electric field times the infinitesimal volume element dV. We have already shown that the energy density of the electric field E is given by 1 over 2 times epsilon naught times E squared, and the volume element dV is simply equal to the surface area S times the displacement delta x. By inserting these expressions into the right-hand side, we obtain 1 over 2 times epsilon naught times E squared times S times delta x. From the law of the conservation of energy telling us that du is completely converted into delta W, we obtain that the force F times the virtual displacement delta x is equal to 1 over 2 times epsilon naught times E squared, times S times delta x. If we divide this equation by S times delta x, we can write the force acting on a unit area of the surface of the charged conductor as 1 over 2 times epsilon naught times E squared. Since the electric field E at the surface conductor is equal to the surface charge density sigma over epsilon naught, the right-hand side can also be written as sigma squared over 2 times epsilon naught. Thus we have obtained the same expressions as the ones derived from the superposition of electric fields due to the charges on the different parts of the surface of the conductor. Since force per unit area is pressure, we can define the electrostatic pressure exerted on a conductor is that the charge exerts on the surface of the conductor, that is the electrostatic pressure is given by 1 over 2 times epsilon naught times E squared or sigma squared over 2 times epsilon naught. We note that the formula obtained for the infinitesimal force stating that dF is equal to 1 over 2 times sigma times E times ds can be integrated over the whole surface of the charged conductor. Then the net force F on a charged conductor is given by 1 over 2 times the surface integral of the surface charge density sigma times the electric field strength E over the surface S of the conductor, or 1 over 2 times epsilon naught, times the surface integral sigma squared over the surface S. As a result, the total electrostatic force acting on a charged conductor is completely determined by the charge distribution over the surface of the conductor or the electric field emanating from or terminating at its surface, and the geometry of the conductor. If more charged conductors are present in a system, then the electric field lines connecting their surfaces produce an attractive electrostatic force between the electrodes. Now we determine the attractive force between the plates of a charged parallel plate capacitor. Instead of calculating the electrostatic forces acting between point charges, we will apply the energy theorem. Let x denote the distance between the plates of the capacitor storing the charges plus q and minus q respectively. In order to increase the distance between the plates by an infinitesimal amount dx, the work dw is required to do against the attractive force F, which is given by F times dx. This infinitesimal work is converted into an infinitesimal change in the energy U of the capacitor, that is du is equal to dw. Then it is also equal to F times dx, and the force F can be written as the derivative of the energy U with respect to the distance x. The energy U of the capacitor is given by the charge Q squared over 2 times the capacitance C of the capacitor, where the capacitance for parallel plate capacitors is equal to epsilon naught times the area A of the plates over the distance x between the plates. Then the energy U is expressed as a function of the instantaneous distance x between the plates. By inserting this expression into the force equation and computing the derivative with respect to x, we can write the force F between the plates of the capacitor as 1 over 2 times q squared over epsilon naught times a, or 1 over 2 times q squared over c times x. Since the distance x is equal to d at a given position of the plate, and the charge q on the plates is equal to the capacitance c times the voltage v between the plates, the force F is given by 1 over 2 times the capacitance c over the distance d, times the square of the voltage v, or 1 over 2 times epsilon naught times the area A over d squared, times the square of the voltage V. This formula shows that the attractive force F between the plates can be determined by measuring the voltage V through the capacitor if the area A of its plates and the distance d between them are known. This relationship is used in the working principle of Thomson's absolute electrometer seen in the figure, which measures voltage and the amount of charge based on the balance between electrostatic and gravitational forces. The electrometer consists of a parallel plate capacitor with a fixed plate and a movable one. The fixed plate is a grounded metal disc and the movable one consists of a smaller disc suspended from the beam of a sensitive balance and a fixed guard ring around the disc. Since the gap between the disc and the ring is extremely small, the electric field has some scattering only at the outer edge of the ring and is uniform between the two plates. As a result, the force formula obtained for parallel plate capacitors can also be applied for the capacitor of the electrometer. If the voltage V is applied to the plates, then the movable plate and the ring attain charge, an opposite charge will be induced on the fixed plate, producing an attractive force F between the plates of the capacitor. The force moving the suspended metal disc can be balanced by placing the weights G in the pan of the balance to restore the position of the moving plate in the plane of the ring. If the magnitudes of the force F and the weight G are equal, then we can replace F by G in the force formula, and express the voltage V as the distance d between the plates times the square root of 2 times the weight G divided by epsilon naught times the area A of the plates. Since the geometry of the parallel plate capacitor of the electrometer precisely specifies the capacitance of the capacitor, the instrument allows one to determine the charge attained by the plates at high accuracy from the measured voltage between the plates. Thomson's absolute electrometer is a specimen of a broader class of devices, where electrostatic forces due to the interaction between bodies with excess charges can be measured by balancing them with non-electrostatic forces. As a result, the amount of electric charge or voltage producing the electrostatic field can also be determined. A measuring device based on this principle is called electrometer, which is the version of electroscopes allowing one to perform quantitative measurements of electric charge. One of the simplest type of electrometers is known as Braun electroscope, normally used for classroom demonstration of electrostatic phenomena. We already presented this instrument as a pointer electroscope without a scale when we discussed how to determine the presence of electric charge on bodies. Now we give a more detailed analysis on the version with a scale, functioning as an electrometer. The housing of the instrument is a grounded metal case, which is cylindrical in shape and has glass windows on both the front and the back sides. A vertical metal rod penetrates the top of the case through some insulation and a curved metal scale is attached to its bottom. The electrical contact at the top of the rod is either a metal sphere or a metal plate. A light needle is connected to the vertical support rod by a pin through its center so that the arm is free to rotate around a horizontal axis. The needle is balanced in a vertical position. If the electroscope is charged through the metal sphere, its vertical rod and needle will attain like charges, producing a repulsive electrostatic force between them. As a result, the needle is repelled by the vertical rod, and rotates to a new equilibrium position at a distance proportional to the amount of charge distributed over the needle and the rod. In its new equilibrium position, the magnitude of the repulsive force is equal to the one of the gravitational force exerted on the arm in the opposite direction. The greater the charge, the greater the deflection of the needle, and we can measure the charge attained by the electroscope or an equivalent voltage by reading this deflection on the calibrated scale. If we want to measure the voltage V of a voltage source between its terminals A and B, then we connect these terminals to the metal sphere of the Braun electroscope and its grounded metal case respectively, as seen in the figure. Here the series of horizontal bars between the nodes A and B in the circuit represent the series of cells of a battery used as the voltage source. The case of the electrometer and its parts insulated from the housing form the plate B and A of a capacitor of capacitance C. Then the plates A represented by the insulated parts of the electrometer will attain the charge Q given by the capacitance C times the voltage V between the sphere and the case, and the plate B represented by the metal case will attain the charge minus Q. A given amount of the charge Q is distributed over the needle of the device. If we denote this amount of charge by Q', then we can write it as some constant K times the charge Q, or K times C times Q, where K is less than unity. On the one hand, the force exerted on the needle is proportional to the charge Q'. On the other hand, this force is also proportional to the electric field strength E between the insulated parts of the instrument and the metal case that is produced by the charges Q and minus Q on them. Since both the charge of the needle and the electric field strength increase with the increasing voltage V, the force exerted on the needle increases as well. As a result, the increasing voltage also increases the deflection of the needle. The scale of the Braun electroscope can also be calibrated by applying known voltages to the instrument, so that the electrometer could directly measure voltage. The range of operation of such devices is between 100 volts to 10,000 volts. If we want to measure the voltage V between the two plates of a charged capacitor of capacitance C, then we connect its plates A and B to those of the capacitor formed by the metal sphere and the parts insulated from the case, and the metal case of the electrometer. As a result, the voltage through the capacitor decreases and the electrometer measures a voltage V' less than the voltage V. The initial charge Q of the capacitor is given by the product of its capacitance C and the voltage V through the capacitor. During the measurement the amount of charge Q distributed over the system does not change, but the capacitor and the electrometer of capacitance C sub L form a series of in parallel. As a result, the capacitance of the system is the sum of the capacitances C and C sub L, and the total charge of the system is equal to the sum of C and C sub L, times the reduced voltage V' between the metal sphere or the plate A and the earth or the plate B. From these two expressions we find that the voltage V through the capacitor can be written as 1 plus the ratio of the capacitance C sub L of the electrometer to the capacitance C of the capacitor, times the voltage V' measured by the electrometer. If the capacitance of the electrometer is much smaller than the capacitance of the capacitor, then the measured voltage is approximately equal to the voltage between the plates of the capacitor. A more sensitive type of electrometer is the unifilar electrometer or string electrometer, utilizing a single fiber or string as the sensitive element of the measurement device. The electric field strength acting on the moving part of the device can be increased independently of the magnitude of the voltage being measured by applying external voltage sources for the electrodes producing the field, as seen in the figure. In the box encasing the apparatus, a fine platinum fiber or a quartz fiber coated with conducting material passes through the electric field E between a pair of metal plates A and B connected to batteries serving as external voltage sources for the field. The voltage V to be measured is applied at the two ends of the fiber, which attains the electric charge Q. As a result, the fiber mounted midway between the two electrodes is deflected by the force of the electric field towards one of the metal plates. The force exerted on the fiber is proportional to the product of the charge Q of the fiber and the magnitude of the electric field strength E. Since the charge Q of the fiber is proportional to the voltage V applied to the fiber, its displacement observed against a scale with a microscope is approximately proportional to the voltage being measured. By applying a proper calibration for the scale, the magnitude of the voltage V can immediately be determined by noting the deflection of the fiber against the scale. The sensitivity of the string electrometer may be increased by adjusting the tension on the fiber and increasing the strength of the field, that is the external potential applied to the electrodes. The later is normally between 50 and 100 volts with respect to ground. We note that there is a bifilar version of the string electrometers where the potential being measured is applied to two fibers passing through the electric field between a pair of electrodes, and the deflection of the fibers due to their mutual repulsion is observed through the eyepiece. The most sensitive and accurate of all the mechanical electrometers are the quadrant electrometers. In these instruments a paddle-shaped aluminum needle with two wings or a vane is independently charged and suspended inside a drum by means of a metal-coated quartz fiber or a torsion fiber made of phosphor bronze. The drum is cut into 4 hollow metallic quadrants supported separately on amber and salting stands, and the insulated quadrants are connected diagonally in pairs by fine copper wires. The potential difference V is to be measured as applied to each pair of quadrants, whereas the vane is usually kept at a constant high potential by connecting it to a battery. When the same potential is applied to the two pairs of quadrants denoted by A and B, the vane rests symmetrically between them. If they have different potentials, then a static electric field E is set up between the quadrants, and a force is exerted on the charged vane. For the potential of the quadrants A greater than the potential of the quadrants B, the vane deflects from the pair A of the quadrants to the pair B of the quadrants. The potential difference V is determined by means of the deflection of the vane toward one pair of quadrants through an angle, which is approximately proportional to the difference of potential between the two pairs of quadrants. The angle of deflection is measured by a beam of light projected on a mirror which is attached to the torsion fiber and reflects the light onto a calibrated scale. In the study of conductors and electrostatic field, we applied Gauss' law stating that the divergence of the electric field strength E is given by its source charge density ρ over the vacuum permittivity epsilon naught, and expressed the field strength as the negative gradient of the electrostatic potential phi to prove Green's reciprocation theorem. As a result, we obtained Poisson's equation for the potential in vacuum stating that the Laplacian of the potential phi is equal to minus the electric charge density ρ over the vacuum permittivity epsilon naught. In general, this equation must be solved as a boundary value problem for the volume of interest with a boundary consisting of the interfaces of different media or conducting surfaces. This can be challenging because normally only the spatial distribution of the source charge is given, whereas the distribution of the induced charges over the conductive surfaces specifying the boundary condition for the problem depends on the potential over the volume of interest, that is, on the solution of the boundary value problem. The most effective approach to solve boundary value problems in electrostatic is based on the principle of superposition already introduced as one of the consequences of Green's reciprocation theorem. Due to this principle, the electrostatic potential phi can be constructed as the sum of a particular solution phi sub p of Poisson's equation for the specified volume charge density, and a general solution psi of Laplace's equation chosen so that the total potential satisfies the specified boundary conditions. The method of images applies such a superposition of the electrostatic potentials in the case of one or more point charges or the distribution of charge along lines in the presence of boundary surfaces, such as conductors or dielectrics. For a few simple geometries, we can replace the actual boundary value problem over the volume of interest V by another problem solved over an enlarged region of the union of V and V' without boundaries, where we place a small number of charges of appropriate magnitudes at appropriate positions in the volume V' external to the region of interest V such that they can simulate the required boundary conditions. In the example shown here, the boundary value problem is to determine the potential phi of a point charge Q in the vicinity of a conductor, either grounded or held at constant potential, which represents a boundary condition for Poisson's equation being solved over the volume V. By applying the method of images, we replaced this problem by another one over the enlarged domain of the union of V and V', where we placed a point charge Q' in the complementary volume V'. We can choose the magnitude of Q' and its position in the volume V' such that we can simulate the boundary condition in the original problem. These fictitious charges external to the volume of interest V are called image charges, and their potentials psi are the general solutions of Laplace's equation inside the volume V that guarantee that all boundary conditions are satisfied for the general solution phi of Poisson's equation over the volume V given by the sum of its particular solution phi sub p and the potential psi. Once the image charges are known, the problem is solved as if the boundary surfaces were not present but with a charge distribution composed of the original charges plus the image charges in the enlarged volume of the union of V and V'. Now we apply the method of images to describe the electrostatic field between charges and conducting surfaces. We start with the simplest example as far as the geometry of the field considered, which is a uniformly charged infinite line and a pair of such lines. We already determined the electric field E due to a uniformly charged infinite line of charge density of lambda at a given point P in the vicinity of the charge line, and we found that its magnitude is equal to lambda over 2 pi times epsilon naught times the distance r between the point P and the line. For a positive charge distributed over the infinite line, the electric field E points radially outward from the line, exhibiting a cylindrical symmetry around it. Because of this symmetry, the field strength E given by the negative gradient of its electric potential phi reduces to minus the derivative of phi with respect to the distance r. Then the electric potential phi is given by minus the integral of the magnitude of E, that is lambda over 2 pi times epsilon naught times r with respect to the distance r. This gives a potential of minus lambda over 2 pi times epsilon naught, times the natural logarithm of the distance r over an arbitrary reference distance r naught of the constant of integration chosen as the null point of the potential. The result shows that the equipotential surfaces of the electric field are cylindrical surfaces around the charged lines for given radii r. Evidently, the electric field lines are perpendicular to these surfaces at each point. Now we consider the electric field due to two parallel uniformly charged infinite lines of opposite polarity of plus and minus lambda, where the distance between the two lines are given by 2 times x0 in the coordinate system with the origin at the midpoint of the two line charges. The xy plane is perpendicular to the line charges and the distance of each charged lines from the origin is equal to x0. We want to determine the potential phi of the field produced by the two charged lines at an arbitrary point P, where the distances r sub plus and r sub minus of the point from the line charges are determined by the Pythagorean theorem. That is, r sub plus is equal to the square root of the square of the y-coordinate of the point plus the square of the sum of the x-coordinate of the point and x0, and r sub minus is given by the square root of y squared plus the square of the difference between x and x0. The potential phi of the field due to the two charged lines at the point P can be constructed by applying the principle of superposition of the individual solutions phi sub plus and phi sub minus of the Poisson's equation given for each of the line charges. If we insert the expression obtained for the potential of an individual line charge into the sum, we can write phi as minus lambda over 2 pi times epsilon naught, times the natural logarithm of r sub plus over r naught, plus lambda over 2 pi times epsilon naught, times the natural logarithm of r sub minus over r naught. As a result, the potential at the point P is given by minus lambda over 2 pi times epsilon naught, times the natural logarithm of r sub plus over r sub minus, where the null point r naught is cancelled out. The equipotential surfaces consist of the points for which the ratio of the distance r sub plus to the distance r sub minus is a constant, say the square root of k, where k is an arbitrary non-negative number. This condition is equivalent to the one stating that the square of r sub plus is equal to k times the square of r sub minus. By substituting the coordinate expressions of the distances into this condition, we can write that y squared plus the square of the sum of x and x0 is equal to k times y squared plus k times the square of the difference between x and x0. We can expand the squares of the sum and the difference of x and x0, and group the terms with the coordinates x and y on the left-hand side of the equation, leaving a constant in the right-hand side. If we divide the resultant equation by 1 minus k, we obtain a simple expression stating that x squared plus y squared minus 1 plus k over k minus 1 times 2 times x0 times x, is equal to minus x0 squared. By completing the square in the left-hand side, we can write the equation stating that the square of the difference between x and 1 plus k over k minus 1 times x0, plus y squared, is equal to 4k times x0 squared over the square of 1 minus k. Now we introduce the notation x sub c defined by 1 plus k over k minus 1 times x0, and the notation y sub c simply set to 0. The notation r sub c can also be defined by 2 times the square root k times x0 over the magnitude of 1 minus k, and we substitute the three constants into the last expression. As a result, we obtain an equation stating that the square of the difference between the x-coordinate and x sub c, plus the square of the difference between the y-coordinate and y sub c, is equal to the square of r sub c, which is the equation of a circle in the xy plane. The center of the circle is defined by the coordinates x sub c and y sub c, whereas its radius is given by r sub c. Then we have found that the equipotential surfaces for the electric field due to two uniformly charged infinite lines are infinite cylindrical surfaces around both of the line charges. The axis of each cylindrical surface lies in the plane y equals 0 and its distance from the origin is given by x sub c. For a fixed distance x0, the constant k determines both the radius r sub c of each equipotential surface and its position x sub c. If k approaches 1, then the centers x sub c of the two sets of equipotential surfaces around the line charges with opposite polarities tend to plus or minus infinity, and their radii r sub c also diverge. As a result, the plane x equals 0 is an equipotential surface and the limit of k approaching 1. The range of k between 0 and 1 describes the equipotential surfaces for x less than 0, that is in the left-hand side of the plane x equals 0, and the values of k greater than 1 represent the equipotential surfaces in the right-hand side of the plane x equals 0. The electric field strength E of the field due to the two line charges is given by the negative gradient of the potential phi with a cylindrical symmetry around the line charges, and we only need to determine the partial derivatives of the potential phi with respect to the x and y coordinates. Since the potential is proportional to the natural logarithm of r sub plus over r sub minus, we compute the derivative of this expression where the prime denotes the partial derivative with respect to either x or y. By applying the chain rule for the differentiation of composite functions, we can write the derivative as the product of the derivative of the natural logarithm of the inner function r sub plus over r sub minus, and the derivative of the inner function. That is, we have r sub minus over r sub plus, times r sub plus prime times r sub minus, minus r sub plus times r sub minus prime over the square of r sub minus. This expression can be written as 1 over the product of r sub plus squared and r sub minus squared, times the difference between r sub plus times r sub plus prime times r sub minus squared, and r sub plus squared times r sub minus prime. Now we use the definitions of the distances r sub plus and r sub minus between any given point and the line charges, and write the partial derivative r sub plus or minus with respect to the x-coordinate as x plus or minus x naught over r sub plus or minus. Similarly, the partial derivative of r sub plus or minus with respect to the y-coordinate is equal to y over r sub plus or minus. These expression can be inserted into the partial derivatives of the natural logarithm of r sub plus over r sub minus with respect to the x and y coordinates. This gives 2 times x naught over the product of r sub plus squared and r sub minus squared, times the x naught squared minus x squared plus y squared, and minus 4 times x naught over the product of r sub plus squared and r sub minus squared, times x times y. If we substitute these derivatives into the partial derivatives of the potential phi, we can write the electric field strength E at a given point as the linear charge density lambda over pi times the vacuum permittivity epsilon naught, times the distance x naught of the charged lines from the origin over the product of the squares of the distances r sub plus and r sub minus between the point and the charged lines, times a vector with the x component given by x naught square minus the square of the x coordinate of the point plus the square of the y coordinate of the point, and with the y component given by minus 2 times the product of the x and y coordinates. The direction of the electric field is perpendicular to the equipotential surfaces which we determine quantitatively. Since the direction of the electric field strength is the tangent to the electric field lines, the derivative of the y-coordinate with respect to the x-coordinate is equal to the y-component of the field strength E over its x-component. By inserting the expressions obtained for the components of the electric field E into this equation, we can write it in the form where the differential of y over y is equal to minus 2 times x times the differential of x over x naught squared minus x squared plus y squared. If r denotes the distance of a point from the origin in the xy plane, that is r squared is equal to the sum of x squared and y squared, then we can convert the equation into another one stating that the differential of the natural logarithm of y is equal to the differential of r squared over x naught squared minus r squared. Here the right-hand side is given by minus the differential of the natural logarithm of the difference between x naught squared and r squared. This separable differential equation can readily be integrated by choosing the constant of integration as 2x naught times cotangent alpha, where alpha is an arbitrary number. As a result, we obtain an equation stating that 2x naught times cotangent alpha times y is equal to minus x naught squared plus r squared. If we substitute x squared plus y squared into r squared and complete the square for the y coordinate, then the result is an equation stating that the square of the x coordinate plus the square of the difference between the y coordinate and x naught times cotangent alpha is equal to x naught squared over the square of sine alpha. This expression is also an equation of circles with the centers lying on the plane x equals 0, whereas the y coordinate of the centers and the radii of the circles are determined by the distance x naught and the constant alpha. Then the equation shows that the electric field lines are circles in the xy plane with the centers on the plane x equals 0, where these circles form cylindrical surfaces running parallel with the charged lines. The intersections of these cylindrical surfaces with the equipotential surfaces, that is the intersections of the two families of circles, demonstrate that the electric field is everywhere perpendicular to the equipotential surfaces, as expected. We have described the electric field due to two uniformly charged infinite lines of opposite polarity running parallel with each other in order to use this problem when we determine an electric field with cylindrical symmetry by applying the method of images. The first example for such a field geometry is the electric field due to a single uniformly charged infinite line near an infinite conducting plane parallel with each other. If we consider the electric field due to an uniformly charged infinite line of charge density lambda at the distance x naught from a conducting plane, then we find the following. The electric field lines emanate from the positive electric charge distributed along the infinite line and terminate at the induced negative charge distributed over the infinite conducting plane. For an electric conductor, these field lines are perpendicular to the planar surface at which they terminate while pointing in the direction opposite of the surface normal. The equipotential surfaces are infinite cylindrical surfaces about the line charge due to the symmetry of the distribution of the charges along the line and over the surface. If we compare the geometry of this electric field with the one in the left-hand side of two uniformly charged infinite lines of opposite polarity at a distance 2 times x naught from each other, then we can see the same distribution and orientation of the electric field lines in space. Motivated by these findings, we will apply the method of images to determine the electric field due to the uniformly charged infinite line near the infinite conducting plane. Since the volume of interest V enclosing the line charge has the boundary at the conducting plane, we need to solve a boundary value problem for Poisson's equation with a source charge given by the linear charge density lambda. Following the method of images, we replace the boundary value problem with a problem where we extend the volume V with the volume V' and place an image charge distribution in V', that is a line charge of the constant charge distribution minus lambda at the distance x0 from the boundary of the volume V. When we derived the potential phi of the pair of infinite line charges with opposite polarity, we applied the principle of superposition and constructed phi as the sum of the individual potentials phi sub plus and phi sub minus due to the positively and negatively charged infinite lines. The potentials phi sub plus and phi sub minus at a given point depend on the distances r sub plus and r sub minus between the point and the line charges. If the domains of these potentials are restricted to the volume of interest V, then the potential phi sub plus is the solution of Poisson's equation with the source charge density ρ sub plus given by lambda times the Dirac delta depending on the x-coordinate plus x0 times the Dirac delta depending on the y-coordinate. This distributional charge density in Poisson's equation is integrated over the volume V. The potential phi sub minus restricted to the volume V satisfies Laplace's equation over V since its source charge density is distributed over the complementary domain V'. As a result, we can identify the potential sub plus restricted to the volume V as the particular solution phi sub p to Poisson's equation with the source charge density ρ sub plus without the boundary condition. The potential sub minus restricted to the volume V is identified as the function psi satisfying Laplace's equation chosen such that the sum of phi sub p and psi gives the solution phi to the original problem. In other words, if the potential phi sub plus due to the uniformly charged infinite line and the potential sub minus due to the image line charge in the complementary volume are restricted to the volume V, then their sum is equal to the potential phi due to the uniformly charged infinite line at a given distance from a conducting plane. Since the potential in this problem is the same as the one due to the pair of uniformly charged infinite lines with opposite polarity, the electric field E at a given point near the infinite line in the infinite conducting plane is also the same as the one derived in the previous problem. Here r sub plus denotes the distance between the point and the line charge, whereas the distance r sub minus between the point and the image charge can be interpreted as a shorthand notation in the formulae. Now we compute the electrostatic force per unit length exerted on the line charge by the induced negative charge over the conducting plane. The force F per unit length L exerted on the infinite line charge is equal to the product of the uniform linear charge density lambda and the electric field E evaluated at the line charge, that is at x equals minus x0 and y equals 0. Although the components of the electric field strength evaluated at the line charge have indeterminate forms, and L'Hospital's rule cannot be applied for functions of two variables to evaluate the limits in general, we can use the principle of superposition to derive the electrostatic force acting on the line charge. We subtract the electric field created by the charged line itself from the net electric field and compute the force produced by the field due to the image line charge of density minus lambda at the distance 2 times x0 from the real line charge. Since the magnitude of the field strength is given by lambda over 2 pi times epsilon naught times the distance between the two charged lines, the magnitude of the force F per unit length L is equal to the square of the linear charge density lambda over 4 pi times epsilon naught times the distance x0 between the charged line and the conducting plane. The force points in the direction of the x-axis towards the infinite plane with the uniform distribution of induced negative charge. Let us also determine the surface charge density sigma of the induced charge over the conducting plane given by x equals 0. We already saw that the surface charge distribution over the surface of a conductor is given by epsilon naught times the directional derivative of the potential along the surface normal. Since the electric field is perpendicular to the conducting plane, the directional derivative of the potential is equal to minus the x component of the electric field strength E evaluated at x equals 0. If we evaluate the expression obtained for the field strength at x equals 0, we can write sigma as minus lambda over pi, times x0 divided by the sum of y squared and x0 squared. The total charge per unit length on the plane denoted by lambda with the subscript tot can be obtained if we integrate the surface charge density at x equals 0 from minus infinity to infinity with respect to the y-coordinate. If we substitute the expression obtained for sigma into the integral, we will have minus lambda times x0 over pi times the integral of 1 over y squared plus x0 squared with respect to y. By factoring x0 squared out from the integral and substituting the variable y of the integration by y over x0, we perform the integration which gives lambda times x0 over pi, times the primitive function 1 over x0 times the inverse of tangent y over x0 evaluated at the limits minus infinity and plus infinity. The evaluation of the primitive function gives minus lambda, that is the total charge per unit length on the plane is just equals the image charge. We can use the example of the pair of infinite line charge of opposite polarity in the method of images to solve other problems where the equipotential surfaces are infinite cylindrical surfaces. The first example for such a geometry is an infinite line charge of uniform charge density lambda at a distance x sub plus from the center of infinite conducting cylinder of radius r, where the line charge is either outside or inside the cylindrical surface. If we inspect the geometry of the electric field produced by the infinite charged line and the induced charge on the infinite conducting cylinder, then we find that the field lines starting from the line charge and ending at the cylinder are perpendicular to the surface of the conductor, whether they are running outside or inside the cylinder. We note that in the latter case the line charge is a free electric charge enclosed by the conducting cylinder, therefore the electric field does not vanish there. The cylinder with the induced charge over it is an equipotential surface, and all the equipotential surfaces are infinite cylinders either enclosing the line charge and the conducting cylinder in two separate families, or enclosing the line charge inside the conducting cylinder. This shows that the geometry of the electric field is the same as the one produced by the two line charges of opposite polarity over the spatial domain of interest, and we can apply the method of images. We therefore replace the boundary value problem over the volume of interest containing the charged infinite line with the boundary at the infinite conducting cylinder by an enlarged volume with an image line charge of opposite polarity. The volume of interest V in the first case is the whole space excluding the cylinder, whereas in the second case V is the space inside the cylindrical surface. Now we extend the volume of interest by supplementing the volume V with its complementary domain V' so that in the union of the volumes V and V' will cover the whole space. In the first case, the complementary volume V' is the domain inside the cylinder, where we place the image line charge of charge density minus lambda. In the second case the complementary volume V' is the whole space outside the cylinder where the image line charge minus lambda is located. The line charge and an image line charge at the distance 2 times x0 produce the same electric field in the volume of interest V as the line charge with the cylinder. We only need to determine the distance x0 for a given distance between the line charge and the center of the cylinder and a given radius of the cylinder. Since the cylinder is an equipotential surface, we can apply the equation describing the circular sections of the cylindrical equipotential surfaces derived for the pair of line charges with opposite polarity. This equation states that the center of these cylindrical surfaces is on the y-axis with the coordinates x sub c given by 1 plus k over k minus 1 times x0, and the radius r sub c of the cylindrical surface is equal to 2 times the square root of k times x0 over the magnitude of 1 minus k. Here the value of k specifies the given equipotential surface. There must exist a value of k for which the equipotential surface in the method of images coincides with the conducting cylinder in the boundary value problem. For such a value k0, we have a condition in the first case stating that the distance x sub plus between the line charge and the center of the cylinder is equal to the sum of the distance x0 and the x-coordinate of the center. In the second case, the condition states that the distance x sub c of the center from the origin is given by the sum of the distances x0 and x sub plus. We can combine these two conditions into one equation and substitute the expression for the x-coordinate of the center into the result. Then we find that the distance x plus is equal to 1 plus k0 over k0 minus 1, times x0, minus or plus x0. Here we use plus for the first case and minus for the second one. Another condition holds for the radius r of the cylinder telling us it is equal to 2 times the square root of k0 times x0 over the magnitude of 1 minus k0. If we raise these two equations to the power of 2 and divide the first equation by the second one, then we can write that x sub plus squared over r squared is equal to the square of the quantity 1 plus k0 plus or minus k0 minus 1 in parentheses, over 4 times k0. After having simplified this expression, we obtain 1 over k0 for the first case and k0 for the second one. As a result, we derive the condition for the parameter k0 that determines the equipotential surface corresponding the conducting cylinder for a given distance between the line charge and the center of the cylinder, where the center and the radius of the cylinder are also given. This condition states that k0 is equal to the ratio of x sub plus squared to r squared for the first case, or its reciprocal for the second one. The second condition holds for the distance x0, which we obtain by inserting the first condition into k0 appearing in the square of the radius r and solving the result for x0. Then we can write that x0 is given by plus or minus x sub plus squared minus r squared over 2 times x sub plus. We can also calculate the distance x sub minus between the image line charge and the center of the cylinder, for which we can write that the distance x sub c of the center from the origin is equal to the sum of x0 and x sub minus for the first case, and express x sub minus as the sum of x0 and x sub c for the second one. If we combine these two equations into one and substitute the expression obtained for x sub c into the result, we can write that the distance x sub minus is given by 1 plus k naught over k naught minus 1 times x naught, minus or plus x naught. By inserting the expression obtained for x naught into the right-hand side of this equation, we find that the distance x sub minus of the image line charge from the center of the cylinder is given by the square of the radius r of the cylinder over the distance x sub plus of the line charge from the center. In other words, the scaling factor between the distances of the line charge and its image from the center of the conducting cylinder is given by the square of the radius of the cylinder. We can also determine the electrostatic force per unit length exerted on the charged infinite line by the charge induced over the surface of the conducting cylinder in the same way as for the line charge near the conducting plane, since both the plane and the cylinder were replaced by an image line charge of opposite polarity. Then the direction of the force exerted on the line charge by the image points towards the image line charge in the plane y equals 0, and the magnitude of the force F per unit length L is equal to lambda squared over 4 pi times epsilon naught times x naught. If we substitute the expression obtained for x naught into the right-hand side of the equation, then we can write the magnitude of the force per unit length as the square of the linear charge density lambda times the distance x sub plus between the line charge and the center of the cylinder, over 2 pi times the vacuum permittivity epsilon naught times the difference between the square of the distance x sub plus and the square of the radius r of the cylinder. This formula becomes singular if the distance x sub plus is equal to the radius r, that is when the line charge is on the surface of the cylinder. If we replace the charged infinite line by an infinite conducting cylindrical surface, then we will have another example for an electric field with cylindrical symmetry. In such a scenario, we consider the electrostatic field due to the charge distributed over two infinite conducting cylindrical surfaces of radii r sub 1 and r sub 2 having their centers the distance x sub 1 apart. The cylinders can either be adjacent, as seen in the figure, or the cylinder of smaller radius can be inside the other one of bigger radius. If any of the cylinders has the charge q, then opposite charge minus q is induced over the surface of the other one, and the electric field lines will emanate from the positively charged cylinder and terminate at the negatively charged one. As in the previous examples, the field lines starting from or ending at the surfaces of the conductors are perpendicular to the surfaces and the conducting cylinders are equipotential surfaces. Then we have the same geometry over the domain of interest for the electric field produced by the two charged cylinders as in the case of the two uniformly charged infinite lines with opposite polarity. In this boundary value problem, the volume of interest V is either the space enclosing the two infinite cylindrical surfaces and excluding their interior, or the space between the two cylindrical surfaces. In both the cases we have two separate boundary conditions for the volume V. Now we apply the method of images by extending the volume of interest with the two domains excluded from the boundary value problem, and placing two image line charges of opposite polarity in each complementary volume. We assume that the volume integrals of the uniform charge densities of opposite polarity of the charged lines give the total amount of the charge q and minus q of the cylinders. In the first case, we extend the volume of interest V with the interior volumes V' and V" of the cylinders, and place the charged infinite lines of charge densities lambda and minus lambda on the x-axis inside the infinite cylinders with polarities corresponding the directions of the field lines in the boundary value problem. In the second case, the complementary volumes V' and V" are the interior of the smaller cylinder and the domain outside the bigger one, respectively. Then the boundary value problem is replaced by the problem involving only two infinite line charges of opposite polarity, and its known solution over the union of the volumes V', V' and V" gives the solution to the boundary value problem restricted to the volume of interest V. The task is to determine where to place the line charges to obtain the same electric field as the one produced by the charged cylinders in the domain of interest. In order to obtain the condition for the position of the line charges equivalent to the charged cylinders, we will compute the distances x sub 1 and x sub 2 of the line charges from the centers of the corresponding cylinders. In the first case, the distance x sub plus of the line charge lambda from the center of the opposite cylinder is given by the difference between the distance d of the centers of the cylinders from each other and the distance x sub 1 of the line charge from the center of the cylinder enclosing the line charge. Similarly, the distance x sub minus of the line charge minus lambda from the center of the opposite cylinder is equal to the difference between the distance d and the distance x sub 2 of the line charge from the center enclosing the line charge. In the second case, the distance sub x plus between the positive line charge and the center of the outer cylinder is given by the sum of the distance x sub 1 between the line charge and the center of the inner cylinder and the distance d. We can also express the distance x sub minus between the negative line charge and the center of the inner cylinder as the distance x sub 2 between the line charge and the center of the outer cylinder minus the distance d. The conditions for the positions of the image line charges follow from the one obtained in the previous example with a single line charge and a single cylinder. The first condition states that the distance x sub 1 between the center of the cylinder of radius r sub 1 and the positive line charge is equal to the ratio of the square of the radius r sub 1 over the distance x sub minus between the negative image line charge and the center of the cylinder. If we substitute the results obtained for the distance x sub minus in the two cases into this ratio, the condition tells us that x sub 1 is given by the ratio of r sub 1 squared to d minus or plus x sub 2, where the upper sign is for the first case and the lower sign is for the second one. The second condition states that the distance x sub 2 between the center of the cylinder of radius r sub 2 and its negative line charge is equal to the ratio of the square of the radius r sub 2 over the distance x sub plus between the positive image line charge and the center of the cylinder. By inserting the expressions obtained for x sub plus into this equation, we can write the ratio as plus or minus r sub 2 squared over d minus x sub 1. The two conditions can be solved for the variables x sub 1 and x sub 2, which gives two second-order algebraic equations. The first one states that x sub 1 squared, minus 2 times a quantity denoted by b sub 1 2, plus r sub 1 squared is equal to 0, whereas the second one states that x sub 2 squared, minus or plus 2 times b sub 2 1, plus r sub 2 squared is equal to 0. The quantity b sub ij is just the shorthand notation of d squared plus r sub I squared minus r sub j squared over 2 times d, where the indices I and j equal 1 and 2 and they are distinct. Then the positions of the line charges are determined by the roots of these equations, and the distance x sub 1 between the positive image line charge and the center of the cylinder of radius r sub 1 is equal to b sub 1 2 minus or plus the square root of the difference between b sub 1 2 squared and r sub 1 squared, and the distance x sub 2 of the negative image line charge and the center of the cylinder of radius r sub 2 is given by minus or plus b sub 2 1 minus the square root of the difference between b sub 2 1 squared and r sub 2 squared. As a result, by applying the method of images for two infinite conducting cylinders of given radii at a given distance from each other, we can replace the two cylinders by two line charges of opposite polarity at given distances from the centers of the cylinders, where the distances can be determined from the radii of the two cylinders and the distance between them. Then the force F per unit length L exerted on the first cylinder by the field due to the opposite image charge minus lambda is equal to lambda squared over 4 pi times epsilon naught times the distance given by the difference between plus or minus d minus x sub 1 and x sub 2. If we insert the expressions obtained for the distances x sub 1 and x sub 2 into the right-hand side, the force per unit length can be written as the square of the linear charge density of the image charges over 2 pi the vacuum permittivity epsilon naught times the square root of the difference between b sub ij squared and r sub I squared, where the indices I and j are equal to 1 and 2 for the first case and 2 and 1 for the second one. Now let us apply the method of images to determine the electric field due to some systems involving a point charge. The first example for such a system is a positive point charge q at the distance x sub plus from the center of a conducting sphere of radius capital R at zero potential. If the distance x sub plus is greater than the radius capital R, the point charge q is outside the sphere as seen in the figure, otherwise the point charge is inside the sphere. In both the cases, the field lines emanating from the point charge and terminating at the conducting sphere are perpendicular to the surface of the sphere since it is an equipotential surface. When we determine the electric field due to the charge q and the induced charge on the grounded sphere, the volume of interest V is the domain outside the sphere in the first case, and the domain inside the sphere in the second one. In this boundary value problem we need to find the potential that vanishes over the sphere representing the boundary of the volume of interest V. We will use the method of images to replace the boundary value problem with another one by extending the volume of interest V with the volume V' either inside or outside the sphere, and place a negative charge q' in the volume V' at the distance x sub minus from the center of the sphere. The superposition of the electric fields due to the point charge q and the image point charge q' is the solution of the boundary value problem over the volume of interest V, provided it gives a zero potential over the grounded sphere. This condition can be used to determine the distance x sub minus and the amount of charge q' for given values of the distance x sub plus, the radius capital R and the amount of charge q. The electric potential phi due to the charge q and its image charge q' is given by the sum of the potentials generated by each of the point charge, that is the potential phi at the point P is equal to 1 over 4 pi times the vacuum permittivity epsilon naught, times the charge q over the distance R sub plus of the point charge q from the point P, plus 1 over 4 pi times epsilon naught, times the charge q' over the distance R sub minus of the image point charge q' from the point P. If theta denotes the angle between the x-axis and the direction of the point P from the center of the sphere, then we can apply the law of cosines, and write the square of the distance r sub plus as the square of the distance r of the point P from the center of the sphere, plus the square of the distance x sub plus between the point charge q and the center of the sphere, minus 2 times r times x sub plus times cosine theta. Similarly, the square of the distance r sub minus can be written as r squared, plus the square of the distance x sub minus between the point charge q prime and the center of the sphere, minus 2 times r times x sub minus times cosine theta. Now we apply the condition stating that the potential phi over the surface of the sphere must vanish, that is, the sum of the two fractions is equal to 0 when it is evaluated at the points for which the distance r is equal to the radius R of the sphere. The condition reduces to the equation stating that q over r sub plus evaluated at the radius R is equal to q prime over r sub minus evaluated at the radius R. Since we express the squares of r sub plus and r sub minus in the terms of the distance r, we will take the square of this equation and use the condition stating that q squared over r sub plus squared must be equal to q prime squared over r sub minus squared when both fractions are evaluated at the radius R. We note that this operation increases the number of the roots of the equation describing the condition, and we need to select the one that has a physical meaning. By substituting the expressions obtained for the distances r sub plus and r sub minus into the condition, we can write the equation stating that q squared times the quantity of R squared plus x sub minus squared minus 2 times R times x sub minus times cosine theta is equal to q prime squared times the quantity of R squared plus x sub plus squared minus 2 times R times x sub plus times cosine theta. This is a general condition which holds for any angle theta. Then it must be true for a given value of theta as well, and we can choose some convenient value to reduce the equation to a simpler form. For theta equals pi over 2, cosine theta vanishes and the condition becomes the equation stating that q squared times the sum of R squared and x sub minus squared is equal to q prime squared times the sum of R squared and x sub plus squared. For vanishing theta, cosine theta is equal to 1 and the condition can be written as the equation stating that q squared times the square of the difference between R and x sub minus is equal to q prime squared times the square of the difference between R and x sub plus. Now we have two equations with the unknown quantities x sub minus and q prime, which will be solved for these two quantities if x sub plus, R and q are given. We can eliminate q and q prime from these equations by dividing the first equation by the second one, and simplify the result by multiplying the fractions on both sides by the product of their denominators. After expanding the square of the sums and further simplifying the result, we obtain a second-order algebraic equation in the distance x sub minus of the image point charge from the center of the sphere stating that x sub minus squared, minus a constant b times x sub minus, plus R squared is equal to 0, where b is defined by x sub plus times the quantity of 1 plus the square of the ratio of R to x sub plus. The roots of the second-order algebraic equation are then given by b over 2, plus or minus 1 over 2 times the square root of the difference between b squared and 4 times R squared. As already mentioned, we need to drop one of the roots of this equation since it is non-physical. The position of the image point charge q prime described by the distance x sub minus must be in the volume v prime complement to the volume v enclosing the point charge q. If we choose the negative sign, then this condition holds and the position of the image point charge described by its distance x sub minus of the from the center of the grounded sphere can be written as the square of the radius R of the sphere over the distance x sub plus. Now we can substitute this result into the first condition of the pair obtained by fixing the angle theta, and express the amount of the image point charge q prime as minus the ratio of the radius R to the distance x sub plus, times the amount of the point charge q. The negative sign indicates that the inducing charge q and the image charge q prime always opposite charges. These formulae hold for both the cases. The image charge q prime is always placed in the volume v prime outside the region of interest, regardless of whether the charge q is located outside or inside the sphere. The distance x sub minus of the image charge from the center of the sphere has a similar scaling property with the radius and the distance of the inducing charge from the center as the one found in the case of a uniformly charged infinite line near an infinite conducting cylinder. The ratio of the radius R to the distance x sub shows that the point charge located outside the sphere has always the greater magnitude, regardless of whether it is the inducing charge or the image charge. The different magnitudes for charge indicate that not all the electric field lines emanating from the point charge placed outside terminate at the sphere. Some of them go around the sphere and terminate at infinity. We note that as the inducing charge q is brought closer to the sphere, the image charge q prime grows in magnitude and moves from the center of the sphere towards its surface. When the point charge q is just outside the surface of the sphere, the image charge q prime is equal and opposite in magnitude and lies just beneath the surface. By applying the method of images, we have determined the electric potential due to the point charge near the grounded sphere in the volume of interest V, which allows us to calculate the electric field strength expressed as the negative gradient of the potential in a spherical coordinate system with the origin at the center of the sphere and the angle theta chosen as its polar angle. The negative gradient of the electric potential phi has the following form. The radial component of the electric field strength E is given by minus the partial derivative of the potential phi with respect to the radial coordinate r. Its polar component is equal to minus 1 over the radial coordinate r, times the partial derivative of the potential phi with respect to the polar angle theta, and its azimuthal component is given by minus 1 over r times sine theta, times the partial derivative of the potential phi with respect to the azimuthal angle phi. As already seen, the electric potential phi of the system at a given point P is the superposition of the Coulomb potentials due to the positive inducing charge and the negative image charge, where the potentials are inversely proportional to the distance r sub plus and r sub minus of the point charges from the point P. The square of the distance r sub plus or minus is equal to r squared plus x sub plus or minus squared, minus 2 times r times x sub plus or minus times cosine theta, as seen in the figures. Then we can derive the components of the electric field strength by computing the partial derivative of r sub plus or minus raised to the power of minus 1. By inserting the expressions for r sub plus and r sub minus into their partial derivative with respect to the distance r, we can write it as minus the ratio of r minus x sub plus or minus, times cosine theta to the cube of r sub plus or minus. Similarly, the partial derivative of the r sub plus or minus raised to the power of minus 1 with respect to the polar angle theta, is given by minus the ratio of r times x sub plus or minus, times sine theta to the cube of r sub plus or minus. If we substitute this result into the negative gradient of the potential phi, the components of the electric field strength E can be written as follows. Its radial component is equal to 1 over 4 pi times epsilon naught, times the sum of the distance r minus the distance x sub plus times cosine theta over the cube of the distance r sub plus times the charge q, and the distance r minus the distance x sub minus times cosine theta over the cube of the distance r sub minus times the charge q prime. Its polar component is given by 1 over 4 pi times epsilon naught, times the sum of x sub plus sine theta over the cube of the r sub plus, and x sub minus sine theta over the cube of the r sub minus. Its azimuthal component vanishes since the potential does not depend on the azimuthal angle phi. In order to summarize our findings, we show the potential phi given by the sum of the potentials due to the point charges q and q prime again, together with the expressions of the distance x sub minus of the image charge from the center of the sphere and the amount q prime of the image charge in the terms of x sub plus, capital R and q. The vanishing azimuthal component of the electric field and the independence of these equations of the azimuthal angle shows the axial symmetry of the electric field about the axis connecting the 2 point charges with each other, that is about the x-axis passing through the point charge q and the center of the grounded sphere. We can also determine the electric field strength E at the surface of the sphere. The distance x sub minus of the image charge q prime from the center of the sphere, that is from the origin of the spherical coordinate system, was expressed as the square of the radius capital R of the sphere divided by the distance x sub minus of the inducing charge q from the center of the sphere. If we suppose that the point P is located on the surface of the sphere and applying this equation, we can write the distance r sub minus of the point P from the image charge q prime as the ratio of r to x sub plus, times the distance r sub plus of the point P from the inducing charge q. Since the image charge q prime is also given by the ratio of r to x sub plus times the charge q, we can substitute these two equations into the components of the electric field strength E to describe the electric field over the surface of the grounded sphere. Then we find that the radial component of the field is given by 1 over 4 pi times epsilon naught, times q over the cube of r sub plus times capital R, times the difference between capital R squared and x sub plus squared while its angular components vanish. This result confirms that the electric field lines are perpendicular to the equipotential surface of the grounded sphere, as we expected. We can also apply the theory of images together with Coulomb's law to determine the force exerted by the charge q on the sphere with its induced charge represented by the image charge q prime. Since the distance between the inducing charge q and the image charge q prime is given by the difference between the distances x sub plus and x sub minus, the component of the electrostatic force F acting between the point charges in the direction of the x-axis is equal to 1 over 4 pi times epsilon naught, times the product of the charges q and q prime divided by the square of the difference between x sub plus and x sub minus. If we insert the expressions obtained for x sub minus and q prime into the right-hand side of the equations, then we obtain minus 1 over 4 pi times epsilon naught, times x sub plus times capital R times q squared over the square of the difference between x sub plus squared and capital R squared. The formula shows that the electrostatic force is an inverse cube law for large separation of the point charge q from the grounded sphere, where the ratio of capital R squared to x sub plus tends to 0. If the inducing point charge is close to the sphere, that is the ratio of capital R to x sub plus tends to 1, then the electrostatic force is proportional to the inverse square of the distance away from the surface of the sphere. As we have already seen, the surface charge density over an equipotential surface is given by the vacuum permittivity times the normal component of the electric field at the surface. Now we use this relationship to determine the surface charge density and the total induced charge over the grounded sphere near the point charge. The surface charge density sigma is evaluated over the equipotential surface given by the radial coordinate r equals the radius capital R of the sphere, and the normal component of the electric field E is equal to its radial component at the surface of the sphere. If we substitute the radial component of E obtained by evaluating the electric field strength at the radius capital R, then we can express sigma as the charge q over 4 pi times capital R, times the difference between the square of capital R and the square of x sub plus, over the quantity of the square of capital R plus the square of x sub plus minus 2 times capital R times x sub plus times cosine theta, raised to the power of 3 over 2. The angular dependence of both the radial component of the electric field strength and the distribution of the electric charge density over the surface of the sphere indicates that the charge distribution is not necessarily uniform over an equipotential surface but always static, as seen in the case of the previous examples of electric fields with cylindrical equipotential surfaces. The total induced charge over the surface of the grounded sphere can be obtained by integrating the surface charge density sigma over its surface, where the surface area element is given by 2 pi times the square of the radius capital R times sine theta times d theta, and the expression is integrated with respect to the polar angle theta from 0 to pi. If we substitute the expression derived for the surface charge density sigma into the integral, then we can write the total charge over the sphere as q over 2 times the difference between capital R squared and x sub plus squared, times the integral of capital R times sine theta over the cube of R sub plus evaluated at capital R with respect to theta from 0 to pi. As the figures illustrating the two cases show, the square of R sub plus is equal to R squared plus x sub plus squared minus 2 times R times x sub plus times cosine theta. The differential of R sub plus evaluated at capital R is therefore given by capital R times x sub plus over R sub plus evaluated at capital R, times sine theta times d theta. We can use this expression to replace the variable theta of the integration by R sub plus, and write the total charge as q over 2 times the difference between capital R squared and x sub plus squared over x sub plus, times the integral of 1 over R sub plus squared with respect to R sub plus from R sub plus evaluated at R equals capital R and theta equals 0. To R sub plus evaluated at R equals capital R and theta equals pi. The primitive function of the integral is given by minus 1 over R sub plus evaluated at the lower and upper limits of the integral. The evaluation of the primitive function gives minus the difference between 1 over the square root of the quantity of capital R squared plus x sub plus squared plus 2 times capital R times x sub plus, and 1 over the square root of the quantity of capital R squared plus x sub plus squared minus 2 times capital R times x sub plus. Then the terms in the brackets can be written as the difference between 1 over capital R plus x sub plus, and 1 over x sub plus minus capital R. If we simplify this expression, then we find that the total charge over the surface of the grounded sphere is equal to minus the radius capital R over x sub plus, times q, that is the image q prime, as we expected. We note that in the two cases of the induced charge outside or inside the sphere, the sign of the surface charge q prime and the direction of the electric field E are opposite over the sphere, as in the previous examples of charged lines and conducting cylinders producing electric fields with cylindrical equipotential surfaces. Now we use the results obtained for a point charge near a grounded sphere to solve another problem by replacing the sphere with a plane. We can determine the electric field due to the point charge q at the distance x0 from a grounded plane as the limiting case of the previous problem if the radius of the grounded sphere becomes infinite. The electric field lines emanating from the point charge q terminate at the grounded plane and they are perpendicular to the phi equals 0 surface, that is, the field lines are parallel with the x-axis at x equals 0. The family of the equipotential surfaces enclosing the point charge approach the vertical plane of the grounded plane at x equals 0 as the electric potential phi tends to 0, and the grounded plane represents the boundary condition for the problem considered in the volume of interest V. As in the previous problem with the grounded sphere, we apply the method of images by dropping the boundary condition and supplementing the volume of interest with the volume V' enclosing the image charge Q' located on the x-axis. This problem can be considered as the limiting case of the previous one, where the radius R of the grounded sphere tends to infinity, and the distance x sub plus of the point charge Q from the center of the sphere also becomes infinite. Then the relation stating that distance x sub plus is equal to the distance x naught plus the radius R still holds. We can evaluate the amount of the image charge Q' given by minus R over x sub plus, times Q in this limit, where x sub plus is given by R plus x naught. The fraction can be written as 1 over 1 plus x naught over R, which becomes minus Q since the limit of the fraction is equal to 1. We also evaluate the distance x sub minus of the image charge Q' from the center of the infinite sphere given by R squared over x sub plus. Here x sub plus is equal to the sum of R and x naught, and the fraction can be written as R times the quantity of 1 over 1 plus the ratio of x naught to R. Since x naught over R vanishes as R approaches infinity, we can apply the Taylor expansion of the fraction at x naught over R at 0. Then we have R times the alternating sum of 1, x naught over R, x naught over R squared, x naught over R cubed and so on. If we multiply each term in the infinite sum by R, then all the terms vanish as R tends to infinity, except the first two terms, which gives R minus R times x naught over R, that is R minus x naught. These two expressions evaluated at the limit of R of the grounded sphere approaching infinity show that in comparison with the magnitude and the position of the inducing charge Q, the image charge Q' is of equal magnitude but opposite polarity and symmetrically located on the opposite side of the grounded plane. The reflection symmetry of the point charges around the grounded plane illustrates why this approach to derive the solution of Poisson's equation of simple boundary value problems is called the method of images. Now we determine the electric field at a given point P at the distance r sub plus and r sub minus from the point charges Q and Q'. We will use the cylindrical coordinate system to describe the electric field because of its axial symmetry about the x-axis. The radial coordinate ρ of the point P is given by its distance from the symmetry axis, and the x-coordinate plays the role of the vertical coordinate normally denoted by z. Then the square of the distance r sub plus between the point P and the point charge Q is equal to ρ squared, plus the square of the sum of x and x naught. Similarly, the square of the distance r sub minus between the point P and the image charge Q' is equal to ρ squared, plus the square of the difference between x and x naught. As in the previous problems where the method of images is applied by introducing an image charge, the electric potential phi at the point P given by the superposition of the Coulomb potentials of the point charges Q and Q' is equal to 1 over 4 pi times epsilon naught, times Q over r sub plus, minus 1 over 4 pi times epsilon naught, times Q over r sub minus. Here we substituted minus Q for the amount of charge Q', and the distance r sub plus or minus is equal to ρ squared plus the square of x plus or minus x naught. Since the electric field strength E is the negative gradient of the electric potential phi, we will determine its components in the cylindrical coordinate system adapted to the symmetry of the problem. The radial component of the electric field is equal to minus the partial derivative of phi with respect to ρ. The azimuthal coordinate of E is given by minus 1 over ρ times the partial derivative of phi with respect to the azimuthal angle phi about the symmetry axis, whereas its vertical coordinate is equal to the partial derivative of phi with respect to the axial coordinate z, which is denoted by x in this problem. First we calculate the partial derivative of r sub plus or minus raised to minus 1 with respect to the radial coordinate ρ, which gives minus ρ over the cube of r sub plus or minus. Then we determine the partial derivative of r sub plus or minus raised to minus 1 with respect to the x-coordinate, and we obtain minus the ratio of x plus or minus x naught to the cube of r sub plus or minus. By substituting these equations into the negative gradient of the potential, the electric field strength E at the point P due to a point charge Q at the distance x naught from a grounded plane can be written as Q over 4 pi times epsilon naught, times a vector with the following components in the cylindrical coordinate system with the axis passing through the point charge and perpendicular to the plane. The radial component of the vector is equal to the difference between the distance ρ of the point P from the symmetry axis over the cube of the distance r sub plus between the point P and the point charge Q, and ρ over the distance r sub minus of the point P from the image charge Q'. The azimuthal component of the field vanishes due to its axial symmetry, whereas its vertical component is given by the difference between the x-coordinate of the point P plus x naught over the cube of r sub plus, and x minus x naught over the cube of r sub minus. Since the distance r sub plus is equal to the distance r sub minus for x equals 0, we can immediately see from this expression that the radial component of the electric field vanishes at x equals 0, that is, the field is perpendicular to the plane as required. As it was seen in the previous examples, the surface charge density of the induced charge over the infinite grounded plane is given by the product of the vacuum permittivity and the normal component of the electric field. That is, the surface charge density sigma evaluated at x equals 0 is equal to minus epsilon naught times the x component of the electric field strength evaluated at x equals 0. The minus sign is applied here since the surface normal points in the negative x direction. If we determine the electric field E over the grounded plane, that is for the vanishing x coordinate, then its component pointing in the direction of the x-axis can be written as q over 2 pi times epsilon naught, times x naught over r sub plus cubed at x equals 0. By substituting this expression into the equation, we can evaluate r sub plus at x equal in the dominator of the fraction. Since r sub plus squared is equal to rho squared plus the square of the sum of x and x naught, r sub plus at x equals 0 reduces to the square root of the sum of rho squared and x naught squared, and we obtain minus q over 2 pi, times x naught over the square of the distance rho plus x naught squared to 3 over 2. This formula shows that the density of the induced charge on the infinite plane has a maximum at rho equals 0, that is at intersection of the x-axis and the plane, and decreases with the distance rho from the point of intersection. The total charge on the grounded equipotential plane can be obtained by integrating this surface charge density over the whole planar surface. Here the area element of the integral expressed in cylindrical coordinates is equal to 2 pi times the square of the radial coordinate rho times d rho. If we insert the expression obtained for sigma at x equals 0 into the integral, then the total charge over the plane can be written as minus q, times the integral of x naught over r sub plus cubed at x equals 0, times rho with respect to rho from 0 to infinity. Since the differential of r sub plus at x equals 0 is given by rho over r sub plus, times d rho, we can apply this result to change the variable rho of the integration to the distance r sub plus. Then we can write the right-hand side as minus q times x naught, times the integral of 1 over r sub squared at x equals 0 with respect to r sub plus at x equals 0, where the lower and upper limits of the integral are r sub plus at rho equals 0 and x equals 0, and r sub plus at rho equals infinity and x equals 0. The primitive function of the integral is equal to minus 1 over r sub plus at x equals 0 evaluated at the lower and the upper limits. The evaluation gives minus the limit of 1 over the sum of rho squared and x naught squared as rho tends to infinity, plus 1 over x naught. Since the first term in the brackets vanishes at infinity, the total induced charge over the infinite grounded plane is equal to minus q. This result means that every electric field line that leaves the point charge q terminates somewhere on the infinite plane, that is, no electric flux escapes to infinity. Since the induced charge is equal to the image charge, the electrostatic force exerted on the grounded planar surface can be derived from Coulomb's law, where the force F between the inducing charge and the image charge located on the x-axis at the distance 2 times x naught from each other is equal to minus 1 over 4 pi times epsilon naught, times q squared over the square of 2 times x naught. The force points from the image charge or the plane towards the inducing charge q. Then the Coulomb force F parallel with the x-axis can be written as minus q squared over 16 pi times epsilon naught times x naught squared. We already determined the electrostatic forces between line charges and various conducting surfaces or between a point charge and a grounded sphere. In this example we discuss a simple situation of a point charge exerting force on a grounded infinite plane, where the later can represent the metal plate of an electrode. This simple setup allows us to analyze the role of the electrostatic force between the image charge and the induced charge on the electrode, and we can see that this force prevents the charged particles, in this case electrons, from escaping from the surface of a conductor in electric field. If we apply a uniform electric field E naught on the grounded plane or the plate of the electrode, then a negative surface charge arises over the surface of the electrode, where the field line terminate as there is no electric field in the conductor. By supposing that the electric field lines of the field E naught are perpendicular to the metal plate and point outward from the plane of the electrode, we can write the net force acting on any charged particle Q emitted from the surface of the electrode as the difference between the electric force represented by the external field E naught, and the Coulomb force due to the image charge minus Q appearing in the opposite side of the conducting surface at the same distance pulling the emitted particle back. That is, the net force is equal to epsilon naught times the magnitude of the electric field E naught, minus 1 over 4 pi times epsilon naught, times q squared over the square of 2 times x naught. Now x naught denotes the instantaneous distance of the inducing charge and the image charge from the surface of the electrode. At the distance where the net force vanishes, the Coulomb force due to the image charge become balanced with the external electric field. This distance representing a threshold can be expressed as the square root of the amount of charge Q over 16 pi times epsilon naught times the magnitude of the electric field E naught. If the distance of a charge carrier emitted from the surface of the electrode from the surface is less than this threshold, the net force points towards the surface pulling back the charge carrier. This effect can be associated with the binding energy of electrons trapped in the surface of a conductor on which an electric field is applied. The external field can be strong enough to accelerate electrons beyond this barrier and they will be able to escape from the conducting surface. When the electric field E naught becomes sufficiently large, the electrostatic force exerted on the electrons close to the surface of the electrode can overcome the quantum mechanical binding forces holding the electrons within the electrode. We used the example of a point charge near a grounded sphere to derive the electric field due to a point charge near a grounded plane as its limiting case. We can generalize this example by applying a conducting sphere either with constant electric charge or constant voltage. First we consider the case with the sphere of constant charge Q0, where the point charge Q in the volume V is outside the sphere of radius R at the distance x sub plus from the center of the sphere. By applying the method of images, we placed an image charge Q' inside the grounded sphere with the volume V' at the distance x sub minus from the center on the x-axis connecting the point charge Q with the center. We saw that the distance x sub minus is equal to the square of the radius R over the distance x sub plus, whereas the image charge Q' is given by minus the ratio of R to x sub plus, times Q. Since the total amount of charge on the sphere is equal to Q0, we need to introduce another image charge to produce an electric field over the union of the volumes V and V' such that the conducting sphere is still an equipotential surface and has a constant charge Q0. If we place a new image charge Q' in the center of the sphere, we can apply Gauss's law to determine the amount of the second image charge by using the sphere as a Gaussian surface. The electric flux due to the charge Q0 on the Gaussian surface must be the same as the one produced by the total amount of image charges inside the sphere. That is, the charge Q0 must be equal to the sum of the image charges Q' and Q', replacing the charged boundary surface in the method of images. If we substitute the result obtained for Q' into the sum, we can express the image charge Q' as the surface charge Q0 of the sphere, plus the radius R of the sphere over the distance x sub plus, times the charge Q. The electric potential due to the 3-point charges is given by the superposition of the Coulomb potentials of the individual charges. Then the potential phi at the point P at the distances R sub plus, R sub minus and R from the inducing charge Q, the image charge Q' and the image charge Q' can be written as 1 over 4 pi times epsilon naught, times Q over R sub plus 1 over 4 pi times epsilon naught, times Q' over R sub minus, plus 1 over 4 pi times epsilon naught, times Q' over R. As seen in the figure, the square of the distance R sub plus or minus is equal to the square of the distance R, plus x sub plus or minus squares, minus 2 times R times x sub plus or minus times cosine theta. We already saw that the sum of the first two terms of the potential vanish over the sphere for the expressions for x sub minus and Q' shown here. Then the potential phi over the charged sphere is given by 1 over 4 pi times epsilon naught, times Q' over R. We can also insert the expressions obtained for the image charges Q' and Q' into the second and third terms of the electric potential phi. The result shows that the potentials of the grounded sphere and the charged one only differ in the third term, representing the contribution of the second image charge. This can be seen in the case of the electric field strength E at the point P as well. The components of the electric field in the spherical coordinate system adapted to the x-axis are the same as those of the field derived in the example with the grounded sphere. The only difference is the contribution of the Coulomb force produced by the image charge Q' in the radial component of the field. This force term is proportional to the image charge Q' over the cube of the distance R between the image charge and the point P. As the vanishing azimuthal component indicates, the electric field is still axially symmetric about the x-axis since all the three charges Q', and Q' are on this axis. The principle of superposition can also be applied to determine the electrostatic force exerted on the charged sphere by the point charge Q, where we calculate the force F exerted on the sphere by the point charge as the superposition of the Coulomb forces acting between the charge Q and the two image charges Q' and Q'. The first term describes the force acting between the point charges Q and Q' at the distance of x sub plus minus x sub minus given by 1 over 4 pi times epsilon naught, times Q time Q' over the square of distance of x sub plus minus x sub minus. The second term represents the Coulomb force between the point charges q and q double prime at the distance x sub plus, which is equal to 1 over 4 pi times epsilon naught, times q double prime over the square of distance x sub plus. We already expressed the first term in the terms of the charge q, the distance x sub plus and the radius capital R in the example with the grounded sphere, and we obtained minus 1 over 4 pi times epsilon naught, times x sub plus times capital R times q squared over the square of the difference between x sub plus squared and capital R squared. We can also substitute the expression obtained for q double prime into the fraction in the second term, and write it as 1 over 4 pi times epsilon naught, q times the sum of q naught and capital R times q divided by x sub plus, over x sub plus squared. The opposite signs in the front of the two terms show that the force attracting the charged sphere is reduced by the electric field due to the constant charge q naught over the sphere. Now we discuss the example of a point charge near a conducting sphere with constant voltage. We consider the case of the sphere of constant voltage phi naught, where the point charge q in the volume V is outside the sphere of radius capital R at the distance x sub plus from the center of the sphere. The method of images is applied again by placing an image charge q prime inside the conducting sphere with the volume V prime at the distance x sub minus from the center on the x-axis connecting the point charge q with the center. The distance x sub minus is still equal to the square of the radius capital R over the distance x sub plus, and the image charge q prime is given by minus the ratio of capital R to x sub plus, times q. Since the potential on the sphere is equal to the constant phi naught, we need to introduce another image charge to produce an electric field over the union of the volumes V and V prime such that the conducting sphere is still an equipotential surface of potential phi naught. If we place a new image charge q double prime in the center of the sphere, we can apply Coulomb's law to determine the amount of the second image charge, which tells us that the potential phi naught is equal to 1 over 4 pi times the vacuum permittivity epsilon naught, times q double prime over capital R. Then the image charge q double prime can be written as 4 pi times epsilon naught times the radius capital R times the potential phi naught. The electric potential due to the 3-point charges is given by the superposition of the Coulomb potentials of the individual charges. As in the previous case, the potential phi at the point P at the distances R sub plus, R sub minus and R from the inducing charge q. The image charge q prime and the image charge q double prime can be written as 1 over 4 pi times epsilon naught, times q over R sub plus 1 over 4 pi times epsilon naught, times q prime over R sub minus, plus 1 over 4 pi times epsilon naught, times q double prime over R. The square of the distance R sub plus or minus is equal to the square of the distance R, plus x sub plus or minus squared, minus 2 times R times x sub plus or minus times cosine theta. Since the first two terms of the potential vanish over the sphere for the expressions for x sub minus and q prime shown here, the potential over the sphere is equal to phi naught, as expected. We can also insert the expressions obtained for the image charges q prime and q double prime into the second and third terms of the electric potential phi. Again, the result shows that the potentials of the grounded sphere and this sphere only differ in the last term, here capital R over R times phi naught representing the contribution of the second image charge. The components of the electric field E in the spherical coordinate system adapted to the x-axis are also the same as those of the field derived in the example with the grounded sphere. The only difference is the contribution of the Coulomb force produced by the image charge q double prime in the radial component of the field. This force term is proportional to the image charge q double prime over the cube of the distance R between the image charge and the point P. The electric field is still axially symmetric about the x-axis because all the three charges q prime and q double prime are on this axis. The principle of superposition can also be applied to determine the electrostatic force exerted on the conducting sphere of voltage phi naught by the point charge q, where we calculate the force F exerted on the sphere by the point charge as the superposition of the Coulomb forces acting between the charge q and the two image charges q prime and q double prime. As in the previous example, the first term describes the force acting between the point charges q and q prime at the distance of x sub plus minus x sub minus given by 1 over 4 pi times epsilon naught, times q time q prime over the square of the distance of x sub plus minus x sub minus. The second term represents the Coulomb force between the point charges q and q double prime at the distance x sub plus, which is equal to 1 over 4 pi times epsilon naught, times q double prime over the square of the distance x sub plus. The first term is given by minus 1 over 4 pi times epsilon naught, times x sub plus times capital R times q squared over the square of the difference between x sub plus squared and capital R squared. By substituting the expression obtained for q double prime into the second term, we obtain capital R over x sub plus squared, times q times phi naught. As in the case of the sphere with constant potential, the force attracting the charged sphere is reduced by the electric field due to the constant non-zero potential phi naught over the sphere. Let us summarize the content of this presentation on conductors and electric field. We started with the discussion on the distribution of charge, electric field and potential in conductors. We demonstrated that in equilibrium the electric field vanishes in a conductor and is perpendicular to the surface of the conductor outside the conductor. We also saw that in equilibrium the excess charge is distributed over the surface of a conductor but no charge can be found over the surface of a cavity inside the conductor. Based on these results we established that the electric field is greater over the parts of a charged conductor having more curved surface. That is, the electric field strength near a charged conductor is inversely proportional to the curvature radius of the surface of the conductor. We also discussed the electric point effect as a limiting case of this phenomenon and presented some of its applications, such as field emission microscopes, the van der Graaff generator and the Wimshurst influence machine. We examined what happens to an electrically neutral conductor placed into electric field, and found that the charge carriers in the conductor will be redistributed such that the electric field due to the induced charge cancels the external electric field inside the conductor. The field also vanishes in any cavity of the conductor, providing an electrostatic shielding, as seen in the case of Faraday cages. We define the capacitance of conductors by the ratio of the charge brought to the conductor to the potential attained by charging. It was shown that the capacitance is independent of charge and potential but depends on the geometry of the conductor, and can be increased by applying conductors in pairs placed close to each other. We presented such devices called capacitors, which are designed to store a great amount of electric charge at a low electric potential. The capacitances of parallel plate capacitors, cylindrical capacitors and spherical capacitors were determined together with the net capacitance of capacitors connected in series and parallel. We also introduced a more general description of systems of conductors by defining capacitance matrices for the system. Green's reciprocation theorem was proven as well, which describes the relation between the electric potentials due to different distributions of charge over the same system of conductors. We determined the energy of a charged parallel plate capacitor, and found that the electrostatic energy stored by a capacitor is proportional to the square of the charge on the plate of the capacitor or to the square of the voltage through its plates, where the proportionality constant is determined by the capacitance of the capacitor. By applying this result, we could derive an expression of the energy density of an electrostatic field, and found that it is proportional to the square of the magnitude of the electric field strength. We also showed that the electric force per unit area exerted on a charged conductor in a field is equal to the energy density of the field, and the total force acting on the conductor is given by the surface integral of the charge density over the surface of the conductor. We could use these findings to determine the force between the plates of a parallel plate capacitor, and we saw that it is proportional to the square of the voltage between its plates. Some measuring devices were also presented that apply the electrostatic force exerted on conductors, producing a deflection of a plate as in the case of Thomson's absolute electrometer, a deflection of a needle as in the case of Braun electrometer, a deflection of a fiber as in the case of unfiliar electrometers, or a deflection of a vane in the case of a quadrant electrometer. Since the deflection is proportional to the voltage applied on the electrodes of the devices, this voltage can be measured with a proper calibration of the device. Finally, we presented the method of images, which is a simple approach to determine the electric field and force produced by electric charges near conductors with various geometries exhibiting some symmetry. We saw that the method is based on replacing a boundary value problem in electrostatics by another problem, where we increase the volume of interest and place a limited number of charge at appropriate locations in the enlarged region to simulate the requirements of the boundary condition. We determined the electric field due to a uniformly charged infinite line near an infinite conducting plane and calculated the force exerted on the line charge. We found that the electric field exhibits a cylindrical symmetry about the conducting line. By motivated this fact, we replaced the plane with an infinite conducting cylinder and derived both the electric field and the force for the new problem, where the field still held its cylindrical symmetry. As a generalization of the problem, we calculated the field strength and the force for a parallel pair of charged infinite conducting cylinders. We also considered point charges near or inside a grounded sphere and near an infinite grounded plane. We proved that the electric field in these examples has an axial symmetry about the line passing through the point charge and the center of the sphere, or the line passing through the point charge and perpendicular to the infinite plane. We also studied how the electric field is modified if we apply a charged sphere or a sphere with non-zero constant potential instead of the grounded sphere. We saw that the field still has axial symmetry, but there is some contribution from the charge or the non-zero potential on the sphere, which also modifies the electrostatic force exerted on the sphere.